Imagine being born on a spaceship. The walls around you are the only world you have ever known. Scientists call it a generation ship, but you would just call it home. You did not choose this life. Your grandparents did, and the destination, you will never see it. If you are the kind of person who loves looking at the universe and asking the big questions, please subscribe to the channel. Now let's get started. So if we ever want to reach another star system, not a probe, but actual living, breathing human beings, we have two basic options. Either we figure out propulsion systems so advanced they border on magic by today's standards, or we accept the travel time as it is and build a ship designed not just to carry people, but to sustain an entire civilization across the void for thousands of years. That second option is the generation ship. And right away, before we even talk about what life would be like on board, the engineering challenge alone is staggering. We are not talking about keeping astronauts alive for 6 months on the International Space Station, which is already extraordinarily difficult. We are talking about maintaining a fully self-sufficient, ecologically stable, socially functioning human society inside a closed metal vessel for potentially hundreds of generations. Every calorie of food, every breath of oxygen, every liter of clean water, every gram of medicine, all of it has to either be produced on board or brought along in quantities that stretch the imagination. And here is the brutal truth. We have never come close to doing this. In 1991, an experiment called Biosphere 2 was launched in Arizona. It was designed to be a completely sealed, self-sustaining ecosystem, a kind of dress rehearsal for exactly this kind of challenge. 8 scientists lived inside a massive glass structure covering roughly 1.27 hectares. They had a rainforest, an ocean, a savanna, a desert, and farmland. The idea was to prove that humans could create a closed-loop life support system. It did not go well. Within months, oxygen levels began to drop dangerously, falling from 21% all the way down to 14.5%. That is roughly equivalent to the oxygen level you would experience standing at an altitude of 4,000 meters. The crew developed cognitive impairment. They were struggling to think clearly. They were exhausted. Crops failed. 25 of the 38 vertebrate species inside went extinct. Ants and cockroaches exploded in population. The concrete in the structure absorbed CO2, which nobody had anticipated. Eventually, oxygen had to be pumped in from outside. Biosphere 2 was not a failure in the sense that we learned nothing. In fact, it was arguably one of the most valuable ecological experiments ever conducted precisely because of everything that went wrong. But what it demonstrated, very clearly, is that building a closed, stable, human-sustaining ecosystem is almost incomprehensibly hard. And that was on Earth, with a full support team outside, with the ability to intervene, with modern medical facilities minutes away. On a generation ship, there is no outside. There is no backup. There is no emergency landing. If something goes wrong, truly wrong, you are on your own, somewhere between the stars, with the nearest help potentially thousands of years away in either direction. So we have established the distance problem. We have felt the weight of those numbers. We know that even our fastest spacecraft would take tens of thousands of years to reach the nearest star. And we know that building a closed, self-sustaining ecosystem, even on Earth with every advantage imaginable, nearly broke the people who tried it. But here is where it gets even more layered. Because the ecological challenge, as daunting as it is, might not even be the hardest part of this equation. Not by a long shot. Let us talk about what the universe itself does to the human body when you leave the protection of Earth. Right now, as you sit here watching this, you are being protected by something so enormous and so powerful that most people never think about it: Earth's magnetic field. This invisible shield, generated deep inside our planet's molten iron core, deflects an almost constant barrage of charged particles streaming in from the Sun and from distant corners of the galaxy. Without it, the surface of this planet would be a very different place, possibly uninhabitable. The moment you leave Earth's protective bubble, you step into one of the most hostile radiation environments imaginable. There are two primary threats. The first is solar energetic particles, bursts of high-energy protons and electrons launched by solar flares and coronal mass ejections. These events happen unpredictably. A major solar storm can release energy equivalent to billions of nuclear bombs in a matter of minutes. The second threat is even more insidious: galactic cosmic rays. These are not coming from our Sun. They come from supernova explosions, from neutron stars, from the violent hearts of distant galaxies. They are extraordinarily high-energy particles, some moving at fractions of a percent below the speed of light, and they punch straight through ordinary metal shielding like it is not even there. We know exactly what prolonged exposure to this radiation does to the human body because we have been studying astronauts for decades. The data from NASA, from the European Space Agency, and from the research conducted aboard the International Space Station paints a sobering picture. Cosmic radiation damages DNA. It increases the risk of cancer significantly. It has been linked to cardiovascular disease. But one of the most troubling findings from recent years involves the brain. Studies published using data from astronauts on long-duration missions and reinforced by research on rodents exposed to cosmic ray simulations at NASA's Space Radiation Laboratory suggest that high-energy galactic cosmic rays cause measurable damage to the central nervous system. We are talking about impaired cognition, reduced motor function, and something that researchers describe as cosmic ray dementia, a gradual deterioration of brain function caused by particles punching microscopic holes through neural tissue over time. Scott Kelly, the NASA astronaut who spent nearly a full year aboard the International Space Station, 340 days to be precise, returned to Earth with measurable changes in his DNA expression, fluid shifts around his brain, and changes in his gut microbiome compared to his identical twin brother Mark, who stayed on the ground. That was 340 days in low Earth orbit, where the planet's magnetic field still provides partial protection. A generation ship would be traveling through open interstellar space for centuries. The radiation exposure would be orders of magnitude worse. Now, there are potential engineering solutions being explored. Water walls surrounding the crew compartments with tanks of water, which absorbs radiation reasonably well. Polyethylene shielding, which is actually more effective against cosmic rays than metal because of its high hydrogen content. Electromagnetic shielding, essentially creating an artificial magnetosphere around the ship, has been theorized, but the energy requirements are currently beyond anything we can realistically generate. Some researchers have proposed having most of the crew spend the majority of their time in a heavily shielded central core of the vessel, with only brief excursions into less protected areas. But here is the honest truth: there is no perfect solution with our current technology. Every proposed shielding system is a compromise. You add more shielding, you add more mass, and mass is the enemy of space travel. Accelerating a heavier ship requires exponentially more energy, and on a journey lasting centuries, even a small increase in radiation exposure per year compounds into devastating health consequences across generations. This is not speculation. This is applied physics and radiobiology, and the scientists working on this problem are the first to admit that we are nowhere near a satisfying answer yet. Here is a question that sounds almost philosophical, but is deeply, urgently practical. How many human beings would you need on a generation ship to ensure that humanity, or at least a genetically healthy branch of it, survives the journey? This is called the minimum viable population problem, and researchers have spent considerable time working through the mathematics of it. For a long time, the rough estimate that circulated was around 160 people, a number derived from studies of isolated populations and genetic diversity requirements. But more rigorous modeling has pushed that number dramatically higher. A study published by anthropologist Cameron Smith from Portland State University, one of the more comprehensive analyses of this question, suggested that to maintain sufficient genetic diversity and buffer against disease, accidents, infertility, and random genetic drift, you would want somewhere in the range of 10,000 to 40,000 individuals on board. Other researchers have suggested numbers as low as 2,160, using different assumptions about mortality rates and reproductive patterns. But virtually everyone who has seriously modeled this agrees. A few hundred people is almost certainly not enough. Why does this matter so much? Because of something called inbreeding depression. When a population becomes too small and genetically isolated, individuals inevitably begin to share more and more of their DNA with their potential partners. Over generations, harmful recessive genes, the kind that normally stay hidden because you need two copies to cause a problem, start expressing themselves. Fertility drops, immune function weakens, developmental problems increase. In extreme cases, a genetically bottlenecked population can spiral into what biologists call an extinction vortex, a feedback loop where declining health reduces reproductive success, which further shrinks the genetic pool, which further worsens health outcomes. We have seen this play out in animal populations. The cheetah is one of the most genetically homogeneous large mammals on Earth, the result of a severe population bottleneck tens of thousands of years ago. This lack of diversity makes cheetahs extraordinarily vulnerable to disease. A single pathogen can sweep through a population with virtually no individual variation to slow it down. Now imagine that happening on a generation ship 100 years into a 500-year journey, with no ability to introduce new genetic material from outside, with no genetic banks sophisticated enough to compensate for every possible deficit, with a closed medical system that has to handle complications it may have never encountered before. Some researchers have proposed solutions carrying a frozen genetic library, sperm, eggs, and embryos from thousands of donors could theoretically allow future generations to introduce genetic diversity without needing the physical presence of those donors. The technology for long-term cryogenic preservation of human reproductive material already exists, at least in limited form. Sperm has been successfully cryopreserved for decades. Eggs and embryos are routinely frozen in fertility clinics around the world. But preserving genetic material at cryogenic temperatures, around -196 degrees Celsius using liquid nitrogen, for hundreds of years in the radiation environment of deep space, while maintaining the infrastructure needed to eventually use it, is a challenge of a completely different magnitude. And even if you solve the preservation problem, you are still asking future generations, people who may have grown up knowing nothing but the ship, to make decisions about reproduction based on genetic optimization criteria that were decided by scientists who lived centuries before them. There is something deeply uncomfortable about that, something that starts to feel less like science and more like something else entirely. So we have the radiation punching through the hull. We have the genetic math that demands tens of thousands of people just to keep humanity's DNA healthy across centuries. We have the ecological nightmare of Biosphere, too, reminding us that even a sealed garden on Earth can collapse within months. But now we need to talk about something that does not show up in engineering schematics or population genetics papers, something that does not have a clean equation or a proposed technical fix, something that might actually be the hardest problem of all. We need to talk about what this does to a human mind. Think about your earliest memories. Maybe it is sunlight through a window, the smell of rain, a park, a backyard, a street corner, a beach. Whatever it is, your sense of self, your identity, your place in the world, your understanding of what reality is, was shaped by an environment that was vast, varied, and largely beyond your control. Now imagine none of that exists. You are born on a ship. You grow up on a ship. Every single thing you have ever touched, smelled, tasted, or seen exists within the same few kilometers of enclosed space. The sky above you is a ceiling. The horizon is a wall. The stars you can see, if you are lucky enough to have a viewport, are not destinations. They are decorations, uneachable, unchanging. The same stars night after night for your entire life, slowly drifting as the decades pass, but never truly getting closer in any way you can perceive. What does that do to a person? This is not a trivial question, and psychologists and space researchers have been wrestling with it seriously. The field of confined environment psychology has grown considerably in recent decades, driven in part by long-duration space missions, but also by research conducted in Antarctic stations, submarines, and isolated research outposts, places where small groups of people are cut off from the broader world for extended periods of time. What that research consistently shows is that confinement, monotony, and the absence of natural environments create measurable psychological stress. Studies of Antarctic overwinter crews, small teams who spend months in complete isolation during the polar winter, document a predictable pattern researchers call the third quarter phenomenon. Roughly 3/4 of the way through a mission, psychological well-being tends to dip to its lowest point. People become irritable, withdrawn, and cognitively sluggish. Interpersonal conflicts spike, motivation collapses, and those are people who chose to be there. People who know the mission has a fixed end date. People who can look forward to going home on a generation ship. There is no third quarter phenomenon because there is no clear quarter at all. Most of the people on board will be born into the mission, live their entire lives inside it, and die before it ends. They did not choose this. Their parents did not choose it either. Maybe their great-great-great-grandparents did. But the person scrubbing the water recyclers on deck 7 in year 140, they had exactly as much say in being there as you had in being born in the country you were born in, which raises a question that philosophers have been taking increasingly seriously. Is it ethical to create a generation ship at all? This is where the conversation gets genuinely uncomfortable, and I think that discomfort is worth sitting with for a moment. When the founders of a generation ship mission climb aboard and press the launch button, they are making a decision not just for themselves, but for every single human being who will ever live on that ship. Hundreds of generations of people who do not yet exist. People who will have no ability to opt out, no ability to say, actually, I do not want to spend my life crossing the interstellar void inside a metal cylinder. I would rather stay behind. The philosopher David Bunin and others have written about what is sometimes called the non-identity problem, the philosophical puzzle of whether you can harm someone by bringing them into existence, even into difficult circumstances, because without that decision, they would not exist at all. It is a genuine puzzle, and there are no easy answers. But there is a related question that feels even more pressing in this context. What kind of society forms when you remove choice from the equation entirely? Human history gives us some instructive and sobering parallels. Closed societies, whether they are geographic islands, isolated religious communities, or totalitarian states, tend to develop in ways that would alarm most of us. Power concentrates, orthodoxies harden, the range of acceptable thought narrows. Deviation from established norms becomes increasingly dangerous because the group literally cannot afford internal conflict when survival depends on every single person doing their assigned job. On a generation ship, that pressure would be amplified beyond anything we have experienced on Earth. If the agricultural team stops working, everyone starves. If the water recycling system is sabotaged, everyone dies. If the engineering crew goes on strike, the hull maintenance fails, and the vacuum of space solves the dispute permanently. The stakes of social cohesion are not political or economic. They are existential every single day. That kind of pressure breeds conformity. It breeds surveillance. It breeds a social structure where the individual is subordinated to the collective in ways that we, sitting here on the surface of a planet with seemingly infinite space to spread out, find deeply alien. Some researchers have suggested that a generation ship society might naturally evolve towards something resembling a strict meritocracy, where every person's role is assigned based on skills and genetic fitness rather than personal preference. Others have speculated that it might trend toward a kind of gerontocracy, where elder generations hold disproportionate power because they are the keepers of institutional knowledge. Still others have pointed out that with the right social engineering and cultural design baked in from the beginning, you might be able to sustain a genuinely open, democratic, pluralistic society across the centuries. But that last option requires something that is extraordinarily difficult to guarantee: that the values and governance structures established at launch remain stable and respected across hundreds of generations in the complete absence of any external accountability. Think about how dramatically human societies have changed in just the last 500 years on Earth. With full access to the outside world, with trade and cultural exchange, and the constant pressure of neighboring civilizations, now imagine a society sealed off from all of that, evolving in isolation, shaped only by internal pressures, resource constraints, and the slow drift of cultural memory over time. What do they remember about Earth after 200 years, after 400? Do they still speak the same language their founders spoke? Do they still share the same values? Do they even still believe in their bones that the destination is real, that there is a planet out there waiting for them, that the mission their great-great-great-grandparents launched them on was legitimate and worth the cost of every life lived inside those walls? This is something researchers call mission drift, and it is one of the most underappreciated risks associated with the generation ship concept. The anthropologist and space settlement researcher Cameron Smith, the same researcher we mentioned a while ago in relation to population genetics, has written extensively about the cultural transmission problem. How do you ensure that the knowledge, skills, and motivations necessary to complete a multi-century mission are successfully passed from one generation to the next, and the next, and the next? Across potentially dozens of generational handoffs, it is not just about keeping records. Records can be corrupted, misinterpreted, or deliberately altered. It is not just about education systems, because education systems reflect the values of the people running them, and those people change. It is about maintaining what Smith calls a living, functional relationship with the mission itself, a collective understanding not just of what you are supposed to do, but of why it matters. And here is the thing: on Earth, we are actually quite bad at this, even under ideal conditions. Think about the knowledge that has been lost over human history, the specific techniques used to build the Roman Pantheon, the formula for Greek fire, the navigational methods of the Polynesian wayfinders, which were nearly lost entirely before dedicated cultural preservation efforts brought them back from the edge of extinction. And those were things people were actively trying to preserve in civilizations that had libraries and universities and trade networks and every conceivable external motivation to maintain continuity. On a generation ship, if a critical piece of technical knowledge is lost. If the people who understood how to maintain the fusion reactor all died in an accident in year 87 and their apprentices did not quite learn everything in time, there may be no recovery. There is no calling in an expert from outside. There is no looking it up in a library that still exists somewhere else. Whatever was lost is simply gone, and the consequences ripple forward through every generation that follows. Some researchers have proposed redundant knowledge preservation systems, multiple independent archives, mandatory cross-training across disciplines, cultural rituals built around the transmission of critical technical information. The idea of embedding essential mission knowledge into art, music, and storytelling, the way ancient oral cultures preserved their most important information, has been seriously discussed as a potentially more resilient alternative to purely technical documentation. But even the most optimistic assessments acknowledge that over a journey of several centuries, some degree of knowledge loss is almost certainly inevitable. The question is not whether the ship will change. It is whether, after 300 years of change, the people living on it will still recognize the mission as their own. If you are enjoying this journey, please subscribe to the channel. Every single day, we explore the cosmos using the latest findings from real missions, real telescopes, and real science, and give this video a like. It really helps more curious people just like you find their way here. So we have spent time inside the ship. We have walked its corridors, felt the weight of its walls, understood the psychological pressure of a world with no outside. We have thought about what happens to a society when it is sealed away from the rest of humanity for centuries, when the mission that justified its existence starts to blur and fade at the edges like an old photograph. Now let us zoom out, way out, because the story of the generation ship is not just about what happens inside the vessel, it is also about what is waiting at the other end. And the more we learn about the universe beyond our solar system, thanks to real telescopes, real missions, and real data coming in right now, the more complicated and extraordinary that destination question becomes. For most of human history, the stars were points of light, beautiful, mysterious, but fundamentally unknowable in terms of what might be orbiting around them. That changed in 1992 when astronomers Alexander Wolszczan and Dale Frail announced the first confirmed detection of planets orbiting another star, a pulsar called PSRB 1257+12. It was a strange, almost eerie discovery. Planets circling the corpse of a dead star, bathed in lethal radiation, utterly unlike anything we would call hospitable. But it cracked the door open. 3 years later, in 1995, Michel Mayor and Didier Queloz, who would later share the Nobel Prize in Physics for this work, detected the first exoplanet orbiting a Sun-like star. It was called 51 Pegasi b, and it was a gas giant about half the mass of Jupiter, orbiting extraordinarily close to its host star, completing a full orbit in just over 4 days. It was not a place you would want to live, but it proved that planets around other stars were not just theoretically possible. They were real, and they were out there. What followed was one of the most remarkable scientific revolutions in human history. The Kepler Space Telescope, launched by NASA in 2009 and operating until 2018, stared at a single patch of sky containing approximately 150,000 stars and catalogued the brightness dips caused by planets passing in front of them. The results were staggering. Kepler confirmed the existence of over 2,600 exoplanets and identified thousands more candidates, and the statistical extrapolation from that data suggested something that genuinely rewires your sense of the cosmos. Our galaxy alone likely contains somewhere between 100 billion and 400 billion planets, 100 billion to 400 billion in a single galaxy. and the observable universe contains something in the neighborhood of 2 trillion galaxies, the numbers stop meaning anything at a certain point. They just become poetry. But the key insight is this: planets are not rare. Planets are the default. The universe is absolutely saturated with them, and among those billions of worlds in the Milky Way alone, a significant fraction orbit within what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planetary surface. Now, the Transiting Exoplanet Survey satellite known as TESS, launched by NASA in 2018 and still operating today, has been conducting a far broader survey of the sky, cataloguing exoplanets around the brightest and nearest stars to our own solar system. And one of the most exciting results to come from the broader exoplanet research community in recent years involves a system that you may have heard of: TRAPPIST-1. TRAPPIST-1 is an ultra-cool red dwarf star located approximately 40 light-years from Earth, and orbiting it are 7 confirmed rocky planets, 7 of which 3 are within the habitable zone. 3 planets that could, in principle, have liquid water on their surfaces. The system was characterized in extraordinary detail using the James Webb Space Telescope, the most powerful observatory humanity has ever built, launched in December 2021 and now operating from a point about 1.5 million kilometers from Earth. Early Webb observations of TRAPPIST-1 have been probing the atmospheres of these worlds, or at least trying to determine whether they have atmospheres at all, which turns out to be a genuinely open question given the intense ultraviolet and X-ray radiation that red dwarf stars tend to emit. The results so far are intriguing but not yet conclusive. One of the inner planets, TRAPPIST-1b, appears to have little to no atmosphere based on its thermal emission data. But the story for the others is still being written, observation by observation, as Webb continues its work. 40 light-years, that is roughly 9 times farther than Alpha Centauri. At Voyager 1's current speed, getting there would take something in the range of 680,000 years, even at a hypothetical 10% of the speed of light, which would require propulsion technology far beyond anything we currently possess. The journey would take 400 years. 400 years. That is a generation ship mission, and here is where we arrive at the scenario I promised you, the one that almost nobody talks about enough. Imagine the mission launches. The ship, carrying 10,000 people, or 20,000, or however many the genetic math demands, leaves the solar system and begins its centuries-long crossing of the interstellar void. The destination is a planet in a nearby star system that astronomers on Earth identified as potentially habitable. The spectral data looked good. The orbital parameters were right. The planet was in the habitable zone. 50 years into the journey, back on Earth, astronomers get a better look at that planet. With improved telescope technology, and telescope technology, as James Webb has demonstrated, improves dramatically over decades, they detect something that changes the picture. Maybe the atmosphere turns out to be mostly carbon dioxide with trace amounts of sulfur dioxide. Maybe the surface temperature, properly modeled with updated atmospheric data, turns out to be 400 degrees Celsius. Maybe the planet is tidally locked to its star, with one face in permanent scorching daylight and the other in permanent frozen darkness, and the terminator zone that might be habitable is far narrower and more hostile than originally thought. The people back on Earth know this within 50 years of launch. They send a message to the ship at the speed of light, but the ship is already 50 light-years away, so the message takes 50 years to arrive. By the time the crew receives the news, 100 years have passed since departure. 10 generations have been born and died inside those walls. What do you do with that information? Do you change course? Maybe. If there is a better destination within reasonable range and the ship has enough fuel and supplies to make the correction. But changing course on an interstellar trajectory is not like adjusting your GPS route. The energy required to significantly alter the vector of a vessel moving at a meaningful fraction of the speed of light is almost incomprehensible. Do you continue anyway? Push on toward a planet you now know is probably not what you hoped, on the chance that the updated data is wrong, or that some small part of the world might still be livable, or because turning back is simply not an option given how far you have come and how much fuel you have burned, or, and this is the option that haunts me most, do you simply not tell anyone on the ship? Do the mission controllers back on Earth make the calculation that informing the crew would destroy morale, destabilize the society on board, potentially trigger the kind of social collapse that ends the mission entirely, and decide that ignorance is the more survivable option? This is not a hypothetical designed to be dramatic. These are the kinds of decisions that actual researchers in the field of long-duration spaceflight ethics have been wrestling with. Who has authority over the mission after launch? The people who funded and designed it, who are still alive on Earth for the first generation but eventually die. The crew, their descendants. What governance structure survives a 200-year journey intact? And underneath all of that is a question that cuts right to the heart of what we think we are doing when we talk about sending human beings to the stars. What do we actually owe the people on that ship? Here is something genuinely remarkable. We are living in what astronomers are already calling the golden age of exoplanet science. The combination of Kepler's legacy data, TESS's ongoing survey, and the James Webb Space Telescope's atmospheric characterization capabilities means that right now, today, in real time, our picture of what the universe actually looks like beyond our solar system is changing at a pace that would have been unimaginable to scientists even 30 years ago. In 2023, Webb detected the most detailed atmospheric fingerprint ever obtained for an exoplanet, a world called WASP-39b, a gas giant about 900 light-years away. The telescope found carbon dioxide, sulfur dioxide, water vapor, and sodium in its atmosphere. Not signs of life. This is a hot, bloated gas giant far too close to its star to be habitable, but a proof of concept that atmospheric chemistry can be read from across the galaxy with sufficient instrument sensitivity. The next generation of telescopes, including the extremely large telescope being constructed in Chile's Atacama Desert, which will use a primary mirror 39 meters across and is expected to see first light sometime around the late 2020s, will push this capability dramatically further. The goal, which many astronomers now consider realistic within the next 2 or 3 decades, is to directly image Earth-sized planets in the habitable zones of nearby stars and read their atmospheric biosignatures. Oxygen, methane, water vapor, the chemical fingerprints of life. Think about what that means for the generation ship question. If, sometime in the next 50 years, we detect what appears to be a biosignature on a planet around a nearby star, actual evidence of biology on another world, what does that do to the ethics, the urgency, and the design of a potential interstellar mission? Does it make the mission more compelling? Absolutely. The promise of reaching a living world, a genuinely inhabited, biologically active planet, would be the most powerful motivator in human history. Or does it make it more complicated? Also, absolutely, because a living world is not an empty canvas. It is a place that has its own story, its own ecology, its own 4 billion years of history, and the question of what we have the right to do when we get there is one that nobody has come close to answering. Time. We all experience it the same way, right? A second is a second, a year is a year. You age, I age, everyone on Earth ages at the same rate, and the universe ticks forward in perfect lockstep for all of us simultaneously, except that is not true. It has never been true, and one of the most beautiful, unsettling, and experimentally confirmed discoveries in the history of physics is that time is not a fixed universal constant. It is elastic, it bends, it stretches, and the faster you move through space, the more dramatically it distorts. Albert Einstein figured this out in 1905, and we have been verifying it ever since with increasing precision. It is called time dilation, and it is not science fiction. It is not a thought experiment that exists only on a chalkboard. It is a measured, documented, real phenomenon that we account for every single day in the technology that runs our world. Here is an example you probably did not know about. The GPS satellites orbiting Earth, the ones your phone uses to tell you where you are, move at roughly 14,000 kilometers per hour relative to the surface. Because of their speed and their distance from Earth's gravity well, their onboard clocks run at a slightly different rate than clocks on the ground. Specifically, they gain about 38 microseconds per day relative to ground-based clocks due to the combined effects of special and general relativity. 38 microseconds per day sounds trivial, but GPS works by measuring the time it takes signals to travel between satellites and receivers with extraordinary precision. If you did not correct for relativistic time dilation, your GPS coordinates would drift by roughly 11 kilometers per day. Every navigation system on the planet would be useless within hours. The fact that your phone can pinpoint you to within a few meters is direct, practical proof that Einstein was right now. What happens when you scale this effect up to interstellar velocities? At 10% of the speed of light, a velocity that is already far beyond anything we can currently achieve, but is often cited as a plausible target for advanced propulsion concepts. The time dilation effect is relatively modest. A journey of 40 years in the reference frame of the outside universe would be experienced as approximately 39.8 years by the crew. Barely noticeable, but as you push toward higher fractions of the speed of light, the effect becomes dramatic. At 50% of the speed of light, time on the ship runs at roughly 87% of the rate it does outside. A journey that takes 10 years as measured by someone watching from Earth would be experienced as about 8.7 years by the crew. At 90% of the speed of light, the crew experiences time at roughly 44% the rate of outside observers. At 99% of the speed of light, the crew ages at roughly 14% the rate of the outside universe. And at 99.9% of the speed of light, the time dilation factor becomes so extreme that a journey across the entire Milky Way, 100,000 light-years, could theoretically be completed within a single human lifetime as experienced by the crew. While 100,000 years pass outside, this is not speculation. This is the mathematics of special relativity, confirmed by experiment after experiment, from particle accelerators, where subatomic particles moving at near-light speed decay at dramatically slower rates than their stationary counterparts, to precise atomic clock measurements aboard aircraft and spacecraft. So here is the profound twist this introduces into the generation ship conversation. If you can push a vessel to a significant fraction of the speed of light, let us say somewhere between 50 and 90%, you start to compress the subjective travel time for the crew to the point where a single generation might actually survive the journey, not multiple generations. One, the people who launch might actually live to see the destination. This fundamentally changes the moral equation. It dissolves the most troubling ethical problem, the one about condemning unborn generations to a life they never chose, because there are no unborn generations. The crew who signed up for the mission are the crew who complete it. They age more slowly than the universe around them. They arrive at their destination and they step out. But here is what makes this not a clean solution. Here is the part that puts a completely different kind of chill into the story. When you arrive at your destination after, say, 30 years of subjective travel time at 90% of the speed of light, you have aged 30 years, you still remember Earth, you still remember the people you left behind, you still remember the city you grew up in, the food you loved, the music that made you feel something. But back on Earth, 63 years have passed. Everyone you knew is old. Many of them are dead. The world you left behind has moved on without you in every imaginable way. New governments, new technologies, new art, new crises, new discoveries. The culture that shaped you is now history. The people who trained you, who funded the mission, who waved goodbye at the launch, they are grandparents now, or they are gone. You are a traveler from the past arriving in someone else's future. Except the future you are arriving in is not Earth's future. It is a planet circling a distant star, 40 light years from everyone and everything that made you who you are. And if something goes wrong, if the planet is not what you hoped, if you need help, if you want to come home, you send a message back to Earth and wait 40 years for a reply. The people who answer that message will not be the people who sent you. They will be their great-grandchildren. The loneliness implicit in that scenario is almost impossible to fully process. So if relativistic speeds change the equation this dramatically, why are we not building ships to travel at 90% of the speed of light right now? Because the energy requirements are almost incomprehensible. To accelerate a crude vessel to a meaningful fraction of the speed of light, you need a propulsion system that makes every rocket engine ever built look like a child's toy. Let us put some real numbers on this, because the scale matters. The kinetic energy of a 1,000-ton spacecraft, which is actually quite small for a crude interstellar vessel, given everything it would need to carry, moving at 10% of the speed of light, is roughly 4.5 times 10 to the power of 20 joules. For context, the total energy consumption of all of human civilization in the year 2022 was approximately 6 times 10 to the power of 20 joules. So accelerating even a modest spacecraft to 10% of light speed would require roughly the same amount of energy that the entire human species consumes in a full year, and that is just 10%. The energy required scales dramatically as you approach higher fractions of the speed of light because of the relativistic mass increase, the same effect that makes it impossible to ever actually reach the speed of light, because as you get closer, the energy needed to go faster approaches infinity. Proposed solutions range from the genuinely promising to the deeply speculative. Fusion propulsion, using controlled nuclear fusion reactions to generate thrust, is probably the most technically grounded near-term option, and it is not as far-fetched as it might sound. We are genuinely getting closer to controlled fusion on Earth. The National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition in December 2022, producing more energy from a fusion reaction than the laser energy used to trigger it, for the first time in history. That is a genuine milestone, even if the road from laboratory ignition to a working fusion reactor powering a city, let alone a starship, is still very long. A fusion-powered spacecraft using something called a magnetic confinement system could theoretically achieve exhaust velocities many times higher than any chemical rocket, potentially pushing a vessel to a few percent of the speed of light over very long acceleration periods. Then there is the concept of an antimatter drive. Antimatter is the most energy-dense fuel theoretically possible. When matter and antimatter meet, they annihilate each other and convert 100% of their mass directly into energy, following Einstein's famous equation, A gram of antimatter annihilating with a gram of matter releases energy equivalent to roughly 43 kilotons of TNT. A spacecraft powered by matter-antimatter annihilation could theoretically reach a significant fraction of the speed of light. The problem is that antimatter is extraordinarily difficult and expensive to produce. The entire output of CERN, the European Particle Physics Laboratory in Geneva, produces only a few nanograms of antihydrogen per year. To fuel an interstellar mission, you would need kilograms or tons of the stuff. With current technology, producing a single gram of antimatter would cost something in the range of $62 trillion and take longer than the current age of the universe. There is also the Breakthrough Starshot initiative, announced in 2016 by the late Stephen Hawking and billionaire investor Yuri Milner. The concept is to use powerful ground-based lasers to accelerate tiny, gram-scale spacecraft, essentially microchip-sized probes attached to ultra-thin light sails, to 20% of the speed of light by pushing them with focused light pressure. At that speed, these probes could reach Alpha Centauri in roughly 20 years and send back data. It is a genuinely interesting concept, and there is active research being done on the components, the laser arrays, the sail materials, the miniaturized instruments, but the key word is probes, gram-scale probes. The physics that might work for a centimeter-wide microchip sailing on a laser beam does not scale up to a vessel carrying 10,000 human beings with enough food, water, air, medicine, and genetic diversity to sustain a civilization across centuries. The two problems are completely different in character, and there is one more physical challenge that tends to get glossed over in popular discussions of interstellar travel, but which is absolutely real and absolutely terrifying when you think it through. At a significant fraction of the speed of light, the interstellar medium, the thin scattering of gas, dust, and particles that fills the space between stars, stops being irrelevant background noise and becomes a lethal hazard in the reference frame of a ship moving at, say, 50% of the speed of light. The hydrogen atoms drifting through interstellar space are not drifting anymore. They are hitting the ship at 50% of the speed of light. Each individual hydrogen atom carries the kinetic energy of a high-speed particle in a particle accelerator. At those velocities, even the extraordinarily thin interstellar medium, roughly one hydrogen atom per cubic centimeter on average, becomes a source of significant radiation dose and physical erosion. A 2016 paper by physicists William Edelstein and Arthur Edelstein calculated that at 90% of the speed of light, the flux of interstellar hydrogen atoms striking the front of a spacecraft would deliver a radiation dose of about 500,000 rem per second to anyone standing at the front of the ship. A dose of 500 rem is enough to kill a human being within weeks. 500,000 rem per second is essentially instantaneous obliteration. Shielding helps, but shielding adds mass, and mass is the enemy we keep returning to. Some proposals involve electromagnetic deflection using powerful magnetic fields to push charged particles away from the ship's path. This could work for protons and other charged particles, but neutral hydrogen atoms and interstellar dust grains are not deflected by magnetic fields. They hit whatever they hit. There is also the question of what happens if you run into something larger. A speck of dust massing just a fraction of a gram, impacting the ship at 90% of the speed of light, would release energy comparable to a small explosive. At these velocities, the distinction between a particle and a weapon becomes blurry. None of this is insurmountable in principle. Proposed solutions include forward shields made of ultra-dense materials, electromagnetic deflectors for charged particles, and active detection and avoidance systems for larger objects. But every solution adds complexity, mass, and potential failure, points to a vessel that already cannot afford many failures. So let us take a breath here. Because we have covered a lot of ground, and I want to make sure we are not losing the forest for the trees. We have talked about radiation, about genetics, about psychology, about the elastic nature of time itself, about propulsion systems that would require the entire energy output of human civilization just to get started. And it would be easy at this point to walk away from all of that feeling like the generation ship is a fantasy, a beautiful, terrible fantasy that makes for great science fiction but has no realistic place in our actual future. But I do not think that is the right conclusion, and neither do a growing number of serious scientists, engineers, and institutions who are thinking about this not as a dream, but as a genuine long-term engineering problem, one that we are not going to solve next year, or next decade, or even this century, but one that is worth taking seriously right now, because the decisions we make in the coming generations about how we invest in science and technology will determine whether our descendants ever have the option at all. Let us talk about what a realistic pathway might actually look like, not the Hollywood version, the real one. The first thing to understand is that no serious researcher believes we go from where we are today to launching a crude interstellar mission in one leap. The pathway, if it exists, is a staircase, and the first steps on that staircase are things we are already climbing. Step 1 is robotic exploration. Before we send people anywhere near another star system, we send probes, many probes, increasingly sophisticated probes over decades and centuries that teach us more and more about what is actually out there. The breakthrough starshot concept, whatever its current limitations, represents a genuine early attempt to think seriously about how you accelerate something to a meaningful fraction of the speed of light. Even if the first generation of starshot probes carries nothing more than a camera and a basic spectrometer, the data they return. After the 20-something years it takes them to reach Alpha Centauri, and the 4+ years for their signal to come back, would be the most transformative scientific dataset in human history. We would know for the first time what another star system actually looks like up close. Step 2 is learning to live in space for real, not for 6 months on the International Space Station, not for a year, for decades, permanently. The development of genuinely self-sustaining space habitats, whether in Earth orbit, at the Lagrange points between Earth and the Moon, on the lunar surface, or eventually on Mars, is not just about those specific destinations. It is about developing the life support technology, the closed-loop ecological systems, the social structures, and the medical knowledge that a generation ship would need. Every year that humans spend living in space teaches us something that cannot be learned any other way. NASA's Artemis program, which returned humans to lunar orbit with the Artemis 1 uncrewed test flight in late 2022 and is working toward crewed lunar landings, is part of this staircase. SpaceX's Starship, which completed its first integrated flight test in April 2023 and has been iterating rapidly since, represents a potential step change in the cost of getting mass into orbit. And cost is everything when you are trying to build infrastructure in space. The proposed Lunar Gateway Station, a small modular outpost intended to orbit the Moon as a staging point for deep space exploration, is another rung. None of these things are a generation ship, but all of them are steps in the direction of one. Step 3 is the hardest and the longest, propulsion. This is where the real bottleneck is. Everything else, life support, genetic management, social engineering, psychological preparation, is extraordinarily difficult but theoretically solvable with sufficient resources and ingenuity. Propulsion is the wall, because you cannot compensate for insufficient speed with clever social design. You cannot hack your way past the inverse square law. Either you can generate enough energy to push a vessel to the necessary velocity, or you cannot. The most promising near-term direction is probably nuclear propulsion in some form, nuclear thermal rockets, where a nuclear reactor heats a propellant like hydrogen to extreme temperatures and expels it for thrust, could achieve specific impulses 2 to 3 times better than the best chemical rockets. They have actually been tested before. The NERVA program in the United States ran nuclear thermal rocket engine tests between 1964 and 1972 and demonstrated that the concept works. It was cancelled for political and budgetary reasons, not technical ones. Beyond that, nuclear pulse propulsion, the concept behind the old Orion project, where a spacecraft is propelled by a series of nuclear explosions detonating behind a pusher plate, could theoretically achieve velocities of several % of the speed of light with technology that, remarkably, already existed in the 1960s. The physicist Freeman Dyson, who worked on Project Orion, believed to the end of his life that it represented the most realistic near-term pathway to the outer solar system and potentially beyond. And then, further up the staircase, fusion. Genuine controlled fusion propulsion, using the same basic process that powers the sun, could in principle achieve exhaust velocities an order of magnitude beyond nuclear fission. The progress on fusion energy over the last decade has been genuinely encouraging, not just the National Ignition Facility milestone we mentioned earlier, but the rapid development of private fusion companies like Commonwealth Fusion Systems, TA Technologies and Helion Energy, all of whom are pursuing different technical approaches and all of whom have received serious investment from people who believe fusion power is achievable within the next decade or two. If fusion power becomes a reality on Earth in the 2030s or 2040s, which is not guaranteed but is no longer the perpetual joke it once was, then fusion propulsion for spacecraft becomes a serious engineering project rather than a theoretical exercise. And fusion propulsion changes the entire conversation about interstellar travel timescales. Now, here is something I find deeply moving about all of this, and I want to take a moment to just sit with it. Every single technology we have just talked about, nuclear propulsion, fusion energy, advanced life support, closed-loop ecosystems, genetic preservation, relativistic physics, every single one of these things was completely beyond the imagination of human beings just a few centuries ago. Not just beyond our capability to build, beyond our ability to even conceptualize. The people who built the great cathedrals of medieval Europe had no framework for imagining nuclear fusion. The sailors who first crossed the Atlantic had no concept of DNA, let alone the ability to preserve it at cryogenic temperatures for centuries. And yet here we are. We discovered all of it. We built all of it. We figured it out, piece by piece, generation by generation, through the most remarkable collective intellectual project in the history of life on this planet. Science. We are made of stardust, literally. The carbon in your body, the oxygen in your lungs, the iron in your blood. All of it was forged inside stars that exploded billions of years before our solar system existed. You are the universe looking at itself. And the fact that this particular arrangement of ancient stardust has figured out how to look back at the cosmos, to measure its distances and read its chemistry and feel its age, that is not nothing. That is extraordinary. That is the thing worth holding on to when the scale of the challenge feels crushing, because the generation ship is not really about engineering, not at its deepest level. It is about the question of whether we are the kind of species that stays or goes, whether we look at the vastness of the universe and feel paralyzed by it, or whether we feel, however tentatively and however slowly, drawn toward it. And the answer that human history seems to keep giving, over and over again, across every ocean and every mountain range and every frontier we have ever faced, is that we go. We figure it out. We adapt. We carry our stories with us into the unknown, and we start telling new ones when we get there. Whether that will ever be true of the stars, I genuinely do not know. Nobody does. But the conversation is happening. The science is real. The people working on it are serious. And the universe, as it turns out, is full of places that might be worth going to. Which brings us to something I have been building toward since the very beginning of this video. Something that I think reframes everything we have discussed, every terrifying challenge, every unsolved problem, every ethical dilemma, in a light that feels less like despair and more like the very oldest, most deeply human thing there is, because there is a version of the generation ship story that we have not told yet. The version that is not about the people who suffer through the journey, or the societies that break under the pressure, or the destinations that disappoint. The version about what it means to be the species that tries anyway. The species that looks at 73,000 years of travel time and says, how do we make that shorter? The species that sits with the knowledge that everyone on the ship will die before arrival and asks, is there a version of this where that is not a tragedy? We are going to get into that next, and we are also going to talk about something the scientific community is increasingly taking seriously, a concept that completely sidesteps the generation ship's most devastating problems, that does not require 10,000 people crammed into a metal tube for centuries, and that might actually be more realistic than anything else we have discussed. It involves sleep, a very, very long sleep that's leaf. We spend roughly 1/3 of our entire lives doing it. We still do not fully understand why. We know it is essential. Deprive a person of sleep for long enough and they will die, just as surely as if you deprived them of food or water. We know it consolidates memory, repairs tissue, regulates hormones, clears metabolic waste from the brain. But the deeper question of why consciousness needs to periodically switch off, why the body insists on this daily rehearsal of stillness, that remains one of the genuinely open mysteries of neuroscience. But here is what we do know. In nature, some animals have taken the basic principle of sleep and pushed it to extraordinary extremes. And what they have achieved biologically is something that, if we could replicate it in humans, would completely transform the generation ship equation. Bears hibernate. Most people know that. But what most people do not fully appreciate is what is actually happening inside a hibernating bear's body. Its core temperature drops by several degrees. Its heart rate falls from around 55 beats per minute to as low as 8. Its breathing slows dramatically. Its metabolic rate drops to roughly 25% of normal, and it sustains this state for months at a time, emerging in spring having lost significant body mass, but otherwise fundamentally intact. No muscle wasting of the kind you would expect from months of immobility. No bone density loss, no cognitive impairment. Bears have evolved a suite of biological mechanisms that protect their bodies and brains during this extended period of suppressed activity in ways we are only beginning to understand at the molecular level. Some animals go even further. The wood frog, native to North America, actually freezes solid during winter. Its heart stops, its blood stops circulating, ice crystals form in its tissues. By any conventional definition, it is dead, and then spring comes, temperatures rise, and it thaws and hops away, as if nothing happened. The mechanisms behind this, involving specialized proteins, cryoprotectants like glucose that prevent ice crystals from destroying cells, and a carefully orchestrated shutdown and restart of metabolic processes, are being studied intensively by researchers who see in them potential blueprints for human applications. And then there is the tardigrade. You may have heard of this one. A microscopic animal less than a millimeter long, found in environments ranging from the deep ocean to the highest mountain peaks to the vacuum of space. Under extreme conditions, desiccation, radiation, temperature extremes, even the hard vacuum of space, the tardigrade enters a state called cryptobiosis, It expels almost all the water from its body, replacing it with a sugar called trehalose that forms a glass-like protective matrix around its cells, essentially suspending all biological activity. In this state, it requires virtually no resources. It produces no waste. It does not age, at least not in any conventional sense. It simply waits, and when conditions improve, it rehydrates and resumes life. Tardigrades have survived exposure to open space in experiments conducted outside the International Space Station. They have been revived after decades in a dried state. One study published in 2016 reported reviving tardigrades from a frozen Antarctic moss sample that had been stored for 30 years. Now, none of this means we can put a human being into suspended animation tomorrow. The gap between a tardigrade and a human being is not a small one. We are organisms of almost incomprehensible complexity compared to a half-millimeter invertebrate. The human brain alone contains roughly 86 billion neurons, each connected to thousands of others in a web of staggering intricacy. Preserving that structure, preserving not just the physical hardware but the functional state of a conscious mind. Through decades or centuries of suspended biological activity is a challenge that makes building a fusion reactor look straightforward. But the research is real, it is happening right now, and it is being driven not just by the dream of space travel but by something much more immediate: medicine. Therapeutic hypothermia is already used in hospitals. When a patient suffers cardiac arrest or a severe traumatic brain injury, cooling the body to around 32 to 34 degrees Celsius can significantly reduce the rate of cell death and improve neurological outcomes. The cooling slows metabolic processes, reduces the brain's demand for oxygen, and buys time for interventions that would be impossible if the body were at normal temperature. NASA has been actively funding research into what it calls torpor-inducing transfer habitats, conceptual designs for spacecraft that would keep crews in a hibernation-like state for long-duration missions, dramatically reducing the resources needed and the psychological stress endured. A company called SpaceWorks has produced detailed feasibility studies for NASA on this concept, suggesting that a crew of 6 kept in rotating torpor cycles on a mission to Mars could reduce the required consumables, food, water, oxygen, by 50 to 60% compared to a conventional mission architecture. And a Mars mission is measured in months. An interstellar mission is measured in centuries. The appeal of suspended animation for the generation ship problem is obvious and enormous. If you can put the crew to sleep, genuinely, deeply, metabolically suspended, you do not have a generation ship anymore. You have something closer to a sleeper ship. The people who launch are the same people who arrive. There are no unborn generations condemned to a life they never chose. There is no mission drift, because the crew is not awake long enough to drift. There are no population genetics problems arising from centuries of isolated reproduction, because there is no reproduction during the journey at all. The social complexity, the psychological deterioration, the institutional memory loss, all of it dissolves, and the resource requirements drop precipitously. A metabolically suspended human being needs a fraction of the food, water, and oxygen that an active one does. The ship can be smaller, lighter, simpler. It can carry a skeleton crew, or no active crew at all, with automated systems, managing the vessel and waking small rotating teams for maintenance checks before returning them to suspension. Of course, the problems do not vanish entirely. They transform, because now you have a different set of questions. Can we actually achieve a safe, reversible suspension state in humans that lasts not for hours or days but for decades or centuries? What happens to the brain during that time? Does consciousness simply pause like a video on hold, or does something more complex and potentially damaging occur in the long silence? What is the effect of decades of radiation exposure on a body in metabolic suspension? Does reduced cellular activity provide some protection, as some researchers believe, or does it actually make certain kinds of radiation damage harder to repair because the normal cellular repair mechanisms are also suppressed? And then there is the question that I find the most philosophically interesting of all. If you go to sleep at 30 years old and wake up at 330, if a century of time passes in what feels to you like a night, are you the same person who went to sleep? Your memories are intact. Your personality presumably is intact, but the world you woke into has no continuity with the world you left. Everyone you knew is gone, not just the people, the entire civilization. The languages may have shifted. The cultural references you carry are 3 centuries out of date. You are, in a very real sense, a time traveler, not through your own experience of time, but through the time of everyone else. There is actually a term for this in philosophy and psychology. It is sometimes called temporal displacement, and while it has mostly been discussed in the context of thought experiments and science fiction, the psychological literature on analogous real-world experiences, survivors of long comas, people released after decades of wrongful imprisonment, individuals emerging from severely isolated communities, suggests that the challenge of reintegrating into a world that has moved far beyond your last conscious memory is genuinely profound, not insurmountable, but profound. And on a sleeper ship arriving at a new star system, there is no familiar world to reintegrate into. There is only the ship, your fellow passengers who are equally disoriented, and whatever is waiting outside the hull, which brings us back to something we touched before, but from a completely different angle now. The question of what you find when you get there. Because here is a scenario that has been seriously discussed in the astrobiology and SETI communities, the search for extraterrestrial intelligence, and that I think deserves more attention than it typically gets in conversations about interstellar travel. What if you arrive and the planet is already inhabited, not necessarily by something that built cities or sends radio signals, not necessarily by anything that would recognize you as a fellow traveler across the cosmos, but by life, genuine, carbon-based, biochemically active life, microbes in the soil or in a shallow ocean or floating in an atmosphere, a biosphere that has been quietly evolving on its own for billions of years, completely unaware that anything like you exists, let alone that you were coming. This is not a far-fetched scenario, given what we now know about the prevalence of potentially habitable worlds, given what the James Webb Space Telescope is already beginning to tell us about the atmospheric chemistry of distant planets. The probability that at least some of the worlds in the nearby stellar neighborhood harbor some form of life is, in the view of many astrobiologists, not negligible. We do not know. We cannot know yet with current technology, but it is a serious scientific possibility, not a romantic fantasy. And if it is true, if the planet your ship has spent centuries crossing the void to reach is already a living world, then what? The history of encounters between expanding civilizations and existing ecosystems on Earth is not a cheerful one. We know what happens when a technologically advanced group arrives in a place that is already occupied. We know about introduced species devastating existing ecologies, about pathogens jumping between biological systems that evolved in total isolation from each other, about the irreversible destruction of environments that took millions of years to develop. We carry that history in our conscience, or at least we should. The question of what ethical obligations a generation ship crew would have toward a living world they had traveled centuries to reach is one that the scientific and philosophical communities have barely begun to grapple with. The Committee on Space Research, known as COSPAR, has established planetary protection guidelines for robotic missions, rules about sterilizing spacecraft to avoid contaminating other worlds with Earth microbes, and about protecting Earth from potential extraterrestrial biological material. But those guidelines were written for probes, for machines, not for 10,000 living, breathing, biologically active human beings who have just stepped off a ship after 300 years and desperately need somewhere to live. There is no protocol for that, not yet, and maybe working one out, thinking it through carefully, honestly, with full awareness of what is at stake, is something our generation has a responsibility to start doing now, long before it becomes an urgent practical question, because the universe does not wait for us to be ready. And that thought that the cosmos operates on its own schedule, indifferent to our preparation, magnificent in its scale, patient in its billions of years. There is a photograph, you have probably seen it, but I want you to really look at it again in your mind for a moment. It was taken on February 14, 1990, by the Voyager 1 spacecraft from a distance of approximately 6 billion kilometers from Earth. Carl Sagan had campaigned for years to have NASA turn the camera back toward home before Voyager crossed the edge of the solar system and the shot became impossible. And when they finally did, what the camera captured was this: a pale blue dot, a tiny, almost invisible speck of light suspended in a beam of scattered sunlight, surrounded by the absolute blackness of space. Sagan wrote about that image in a way that I think is worth carrying with you for the rest of your life. He said, "Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." That image was taken from within our own solar system, from a distance that Voyager 1, traveling at 17 kilometers per second, had taken over 12 years to cover, and yet, on the scale of the galaxy, 6 billion kilometers is essentially nothing, a rounding error, a breath. The nearest star is 4.37 light-years away. The galaxy is 100,000 light-years across. The observable universe is roughly 93 billion light-years in diameter. And beyond the observable universe, beyond the sphere of space whose light has had time to reach us in the 13.8 billion years since the Big Bang, the universe almost certainly continues, possibly forever, in directions and dimensions we have no way of perceiving or measuring. We are small, extraordinarily, almost comically small, and the generation ship, in a sense, is the most honest possible confrontation with that smallness. It does not let you look at the stars abstractly, as points of light on a pleasant evening walk. It forces you to feel their distance in your bones. It makes you calculate what it would actually cost, in human lives, in generations of sacrifice, in centuries of endurance, to cross even the tiniest fraction of the void between here and there. And when you feel that weight fully, something interesting happens. At least it does for me, and I suspect it might for you too. The smallness stops feeling like a diminishment and starts feeling like something else entirely, something closer to wonder, because if we are this small and the universe is this vast, and we are nonetheless here, conscious, curious, capable of asking these questions and building these telescopes and writing these equations, then that is not a story of insignificance. That is a story of something almost miraculous. Think about the chain of events that produced you, not just your parents and grandparents, though that chain is extraordinary enough on its own. Go further back. The first human beings, roughly 300,000 years ago in Africa, who looked up at the same stars we see tonight and felt something: curiosity, fear, awe, the stirring of a question that had no name yet. Go further, the first mammals, tiny and warm-blooded, surviving the catastrophic asteroid impact 66 million years ago that ended the reign of the dinosaurs. Not through any special strength or intelligence, but through sheer, improbable luck. Further still, the first vertebrates hauling themselves onto land around 375 million years ago, the first multicellular organisms, the first single-celled life, appearing on this planet sometime around 3.5 to 4 billion years ago, when Earth was a violent, volcanic, barely recognizable world. And before that, the atoms themselves, the carbon, nitrogen, oxygen, and hydrogen that make up every living thing on Earth were synthesized inside stars, massive, brilliant stars that burned for millions of years and then exploded in supernovae, scattering their enriched material across the galaxy. That material coalesced into clouds. The clouds collapsed under gravity, new stars and planetary systems formed, and on at least one of those planets, ours, the chemistry got complicated enough, given enough time and enough energy from a nearby star, to become alive. You are the universe experiencing itself. That is not a poetic metaphor. It is a literal description of what you are. The same hydrogen that was forged in the Big Bang 13.8 billion years ago is sitting in your body right now. The iron in your blood was made in the core of a dying star. You are ancient, you are cosmic, and you are looking out at the universe with the very atoms it gave you, asking questions it has spent billions of years preparing you to ask. The generation ship, viewed through this lens, is not just an engineering project. It is not just a survival strategy or a backup plan for a species worried about extinction. It is the universe reaching out toward itself. It is stardust trying to cross the void between stars, trying to carry the story of life from one small rocky planet to another, continuing the improbable chain of complexity and consciousness that has been building since the very first moments of time. And whether or not we ever actually build one, whether the engineering proves too hard, whether the ethics prove too thorny, whether we find better solutions or decide the stars are simply too far, the fact that we are seriously asking the question says something profound about what we are. No other species we know of has ever done this. No other arrangement of matter and energy in the observable universe, as far as we can tell, has ever looked up at the night sky, measured the distance to another star, calculated what it would take to get there, and begun, however haltingly and imperfectly, to work on it. That might be rare. It might even be unique, at least in this corner of the galaxy, at least at this moment in cosmic history. And that rarity, if it is real, is itself an argument, not a comfortable one, not a simple one, but an argument nonetheless. If conscious, curious, question-asking life is uncommon in the universe, if the chain of events that produces a civilization capable of building telescopes and generation ships is genuinely improbable, then maybe the continuation of that chain matters. Maybe spreading it outward, carrying it to new worlds, ensuring that it does not end with a single planet around a single star is one of the most meaningful things such a civilization could do, not out of arrogance, not out of the assumption that we are the center of anything or the pinnacle of anything, but out of something more humble and more honest, the recognition that consciousness, wherever it arises, is precious, that the ability to ask why is extraordinary, and that a universe capable of producing creatures who wonder at it is, in some way that defies easy articulation, richer than one that cannot. The late physicist Stephen Hawking, who thought about this more carefully than almost anyone, believed that the long-term survival of the human species required us to become a multi-planetary civilization and eventually a multi-stellar one, not because Earth is necessarily doomed on any near-term timescale, but because putting all of our biological and cultural heritage on a single planet is, over cosmic timescales, an almost certain recipe for eventual extinction. Asteroids happen, supervolcanoes happen, gamma-ray bursts from dying stars happen, civilizational self-destruction, as we are perhaps uncomfortably aware, can happen. Spreading out does not make us invulnerable, but it makes us more resilient. It gives the story more chances to continue. And there is something else that the generation ship conversation reveals, something I think about a lot when I look at the broader sweep of human history, every single great journey in our past, every ocean crossed, every continent settled, every frontier pushed back, was undertaken by people who could not fully know what they were getting into. The first humans to migrate out of Africa did not have a map. The Polynesian navigators who crossed the Pacific in outrigger canoes, reading the stars and the swells and the flight patterns of birds, did not know what they would find. The people who sailed west from Europe in small wooden ships were venturing into a genuine unknown, armed with courage and curiosity, and an imperfect but burning desire to see what was on the other side. They went anyway, and the world we live in, for all its flaws and all its unresolved injustices, is the product of that going, of that restlessness, of that refusal to accept the horizon as a final answer. The stars are the next horizon. They are so far away that the journey makes every previous human migration look like a walk across the street. The challenges are so profound that we cannot yet see all the way to the solutions. But the impulse, the deep, ancient, almost biological impulse to look at what is out there and move toward it, that is not going anywhere. It is in us. It has always been in us. It is arguably one of the things that makes us most fundamentally human. And so when I think about the generation ship, when I sit with all of its terror and its beauty and its impossible scale, what I feel, underneath all the rational analysis, is something that I can only describe as recognition. Like hearing a story that was always going to be told. Like watching a river that has been flowing toward the sea for a very long time, moving slowly but inevitably, carrying everything with it. We are going to keep asking these questions. We are going to keep building better telescopes and faster rockets and more sophisticated models of what the universe actually looks like beyond our little corner of it. We are going to keep having the hard conversations about ethics and genetics and psychology and what we owe the people who come after us. And some generation, not ours probably, but some generation is going to face a choice that is more concrete and more urgent than the theoretical exercise we have been walking through today. And when that day comes, I hope the people facing that choice will have thought carefully about everything we have discussed, about the radiation and the genetics and the psychology, about the ethics of the unborn and the rights of existing ecosystems, about the elastic nature of time and the incomprehensible energy requirements of interstellar propulsion, about Biosphere 2 and what it taught us about the terrifying fragility of closed ecosystems, about the pale blue dot, and what it means that we can see ourselves from the outside at all, because understanding the full weight of the challenge is not a reason to give up on it. It is the only honest way to begin. If you are still watching, make sure to subscribe to the channel. Your support means the world to me. There is a question that sits at the edge of everything we have been discussing, and I have been deliberately saving it because I think it reframes the entire conversation in a way that is both exciting and, depending on how you look at it, a little destabilizing. It is a question that the most serious thinkers in artificial intelligence, astrobiology, and the philosophy of mind have been circling for years, and it goes like this. When we finally send something to another star, will it be us? Not us in the sense of human beings with heartbeats and memories and the ability to feel cold and hunger and loneliness, but us in the sense of something we made, something we designed, something that carries, in whatever form makes sense for its architecture, the accumulated knowledge and values and curiosity of the civilization that built it. This is not a fringe idea. It is increasingly a mainstream one in the communities that think seriously about interstellar travel. And the more honestly you confront the biological challenges we have spent the last 8 parts laying out, the radiation, the genetic bottlenecks, the psychological deterioration, the metabolic demands, the sheer fragility of the human body in deep space, the more the logic of it becomes difficult to argue with. Consider what an artificial system optimized for interstellar travel would look like compared to a biological one. It would not need air, it would not need water, it would not need food, or sleep in any conventional sense, or a carefully managed social environment, or genetic diversity, or medical care. It would not experience psychological deterioration from confinement, because confinement is not a concept that applies to a system that does not have a nervous system evolved for open savanna landscapes. It would not age in the way biological organisms age. It would not be damaged by radiation in the same catastrophic way that human DNA is, though radiation can certainly damage electronic systems too, but in ways that are far more predictable, far more repairable, and far more amenable to engineering solutions than biological radiation damage. And perhaps most importantly, it would not die before the mission ends. It would not leave children who did not choose to be there. It would not forget the mission. It would not rebel against it or reinterpret it, or lose faith in it over centuries of isolation. Now, I want to be careful here, because this line of thinking can slide very quickly into assumptions that are not warranted by the current state of the science. We do not have artificial general intelligence. We do not have systems that truly understand in any deep sense the goals they are pursuing or the values they are supposed to embody. The artificial intelligence systems we have today, impressive as they are in specific domains, are not the kind of autonomous, self-directed, genuinely intelligent entities that the interstellar travel scenario requires. They are sophisticated pattern-matching systems, extraordinarily capable in narrow contexts, but brittle in ways that a centuries-long autonomous mission would ruthlessly expose. But the trajectory of the technology is real. And the question of what artificial minds might be capable of in 50 years, or 100, or 200, in the same time frame we are discussing for the development of interstellar propulsion, is genuinely open. Not guaranteed, not inevitable, but open. And when you sit with that openness honestly, the scenario starts to feel less like science fiction and more like a genuine fork in the road ahead of us. There are essentially 3 versions of this that researchers and thinkers have explored. The first is fully autonomous robotic or artificial intelligence missions, probes, or eventually more complex systems sent ahead of any human presence to explore, characterize, and potentially prepare target star systems. This is the most conservative version and the most technically near-term. We already do this in our own solar system. Voyager, Cassini, New Horizons, the Mars rovers. These are all robotic emissaries sent to places we have not yet sent people. Scaling this concept up to interstellar distances is an enormous leap, but it is a leap in degree rather than in kind. The breakthrough starshot concept, whatever its current limitations, is pointing in this direction. The second version is something that researchers sometimes call directed panspermia, not sending machines, not sending people, but sending life itself. Specifically, the kind of life that is extraordinarily robust to the conditions of interstellar space, microorganisms. The idea, which was seriously proposed by the Nobel Prize-winning molecular biologist Francis Crick and his colleague Leslie Orgel back in 1973, is that life on Earth may itself have arrived from elsewhere in the galaxy, deliberately sent by some other civilization on a similar mission. We do not have evidence for this. It remains a hypothesis rather than a confirmed fact. But Crick and Orgel pointed out that it is not obviously ruled out by anything we know. and the idea of deliberately seeding other worlds with Earth life. Engineered microorganisms designed to survive the journey and begin the slow process of biological transformation on a target world is something that astrobiologists have continued to discuss with varying degrees of enthusiasm and concern ever since. The third version is the one I find the most philosophically rich and the most difficult to think about clearly. It involves not choosing between humans and machines, but blurring the boundary between them. The possibility that future interstellar travelers might not be purely biological or purely artificial, but something in between. Humans augmented so extensively by technology that the distinction between the organic and the engineered becomes increasingly meaningless. We are already, in a modest sense, on this path. Cochlear implants restore hearing by interfacing electronics directly with the auditory nerve. Deep brain stimulators treat Parkinson's disease and severe depression by delivering precisely timed electrical pulses to specific brain regions. Retinal implants can partially restore vision in people who have lost their photoreceptors. Research groups around the world are working on more sophisticated brain-computer interfaces, the most prominent being Neuralink, founded by Elon Musk, which received FDA approval for human trials in 2023 and implanted its first device in a human patient in January 2024. The current generation of these technologies is primitive, extraordinarily primitive, measured against what would be needed for the kind of human-machine integration that interstellar travel might ultimately demand. But the direction of travel is clear, and if you project it forward over centuries, if you imagine the biological and technological sciences continuing to advance at anything like the pace of the last 100 years, the destination starts to look very different from the starting point. A crew member on a generation ship 500 years from now might be protected from radiation by engineered biological repair mechanisms that are orders of magnitude more effective than the ones evolution gave us. They might maintain their genetic diversity, not through traditional reproduction, but through sophisticated biotechnological interventions we cannot yet fully conceptualize. They might interface directly with the ship's systems through neural connections that make the boundary between crew and vessel genuinely ambiguous. They might have lifespans measured not in decades but in centuries, not because of any single breakthrough, but because of the cumulative effect of advances in understanding aging at the molecular level. Advances that researchers like David Sinclair at Harvard and Aubrey de Grey have been laying groundwork for over the last several decades. Are those people still human? In what sense? What does human mean when the boundaries have been pushed that far? I do not think these are trick questions with obvious answers. I think they are genuine, open questions that our civilization is going to have to wrestle with increasingly seriously as the century progresses, and the generation ship is, in a strange way, a useful lens for exploring them because it makes the stakes concrete, because it forces the question out of the abstract and into the practical. If you are designing a crew for a 500-year interstellar mission right now, today, what characteristics do you optimize for? Biological resilience, psychological stability, cognitive flexibility, longevity, radiation resistance, the ability to function effectively in extreme isolation over multi-generational timescales. And as you go through that list, you realize that almost none of those characteristics are ones that natural evolution has particularly optimized us for. We are optimized for African savannas, for social groups of roughly 150 people, for lifespans of several decades, for environments with day and night and seasons, and the full sensory richness of a living planetary surface. The gap between what we are and what a generation ship crew would need to be is enormous, and the question of how we close that gap, whether through technology, through biology, through some combination of the two, or through the creation of genuinely artificial minds that carry our values and our curiosity forward without our biological limitations, is arguably the defining question of the next several centuries of human civilization. And underneath all of it, running like a current through everything, is something that I think is easy to lose sight of when you are deep in the technical details. Something that matters more than the engineering, more than the physics, more than the genetics and the psychology and the philosophy, the reason any of this is worth discussing at all, the reason scientists spend careers on it, the reason thinkers lose sleep over it, the reason you are still here watching this, is not really about survival, not at its root. Survival is part of it, yes. The practical case for becoming a multistellar species is real, and it is serious. But I do not think that is what actually moves people when they contemplate the generation ship, when they really sit with it and feel its full weight. What moves people, I think, is the same thing that moved the first human beings who looked up at the stars and felt something they could not name. It is the pull of the unknown, the deep, almost cellular recognition that there is more out there than we can see from where we are standing. That the universe is not a backdrop for our story, it is the story. That we are part of something so vast and so ancient and so indifferent to our comfort, and so breathtakingly, heartbreakingly beautiful that the only sane response is to want to understand it better, to want to go further, to want to see what is on the other side of the dark. The generation ship is a human answer to an inhuman scale. It is imperfect and it is audacious, and it is probably, by any rational accounting, premature. We have not solved the problems we would need to solve to do it safely or ethically or successfully. We may not solve them for centuries, and there is a real argument to be made that we should focus our energy on the world we already have, on the problems that are already urgent, before we start worrying about planets circling other stars. But I also think that the imagination and the ambition that the generation ship represents are not separate from the work of building a better world here. They are part of the same impulse. The same curiosity that asks, how do we cross the stars, also asks, how do we feed everyone on this planet? How do we cure the diseases that are still killing millions of people? How do we build systems that are fair and resilient and worthy of the extraordinary creatures that we are? Science does not choose between these questions. It asks all of them simultaneously with the same fundamental attitude. I do not know yet, but I am going to find out. And that attitude, that relentless, humble, wide-eyed refusal to accept the current limit as the final one, is the most valuable thing our species has ever developed. More valuable than any specific technology, more valuable than any particular discovery, because it is the engine that produces everything else. You are made of stardust. You live on a pale blue dot in the outer arm of a spiral galaxy that contains hundreds of billions of stars, in a universe that contains hundreds of billions of galaxies, that has been evolving for 13.8 billion years and will continue evolving for timescales so large they make that number look trivial. And you are here, right now, thinking about crossing the void between stars, feeling the weight of it, asking whether it is possible and whether it is right and what it would cost and whether it would be worth it. That is not a small thing. That is the universe doing something remarkable with the matter it has been arranging for nearly 14 billion years. Let us talk about something that does not come up nearly enough in the generation ship conversation, and that is the question of governance. Not in an abstract political science textbook kind of way, in the most urgent, visceral, practical sense of the word. Because when you seal thousands of human beings inside a metal vessel and send them into the dark for centuries, the question of who makes the decisions, and more importantly, who has the power to enforce them, becomes a matter of life and death in a way that it simply is not in any earthbound political context. Think about how governance works on Earth right now. Every political system we have ever developed across every culture and every era of human history has operated within a specific set of conditions that we take almost entirely for granted. The existence of geography, the fact that there are borders, territories, places you can go and places you cannot, physical space that can be controlled or contested or fled to, the existence of external accountability, other nations, other communities, international bodies, the court of global opinion, however imperfect, all of those things are in practice. The existence of exit. If things become bad enough, you can leave. You can emigrate, you can relocate, you can find somewhere else that operates differently. And the existence of scale. Most societies large enough to sustain complex governance structures are also large enough to contain genuine internal diversity, competing interests, multiple factions that check each other's power simply by existing. On a generation ship, almost none of those conditions apply. There is no geography in any meaningful political sense. The ship is the entire world, and every cubic meter of it is essential to survival. There are no borders to contest because there is nowhere else to go. There is no external accountability, no international community watching, no press, no outside observers. There is no exit. If you disagree profoundly with the direction the ship's leadership is taking, your options are extraordinarily limited. You cannot leave. You cannot establish a rival settlement on the other side of the mountain. You cannot even, in most realistic ship designs, physically separate yourself from the people you are in conflict with for more than a very short distance, and in terms of scale, even a ship carrying tens of thousands of people is, by the standards of any functioning modern democracy, a tiny community, small enough that the dynamics of small group psychology start to dominate in ways that formal governance structures alone cannot fully manage. What this means practically is that the generation ship is one of the most extreme governance challenges imaginable, and the history of extreme governance challenges on Earth, situations where small groups of people were completely isolated and forced to make existential collective decisions without external support, is genuinely instructive. Even if none of the historical parallels are perfect, consider what happened on Pitcairn Island. In 1789, the mutineers from HMS Bounty, along with a group of Tahitian men and women, settled on Pitcairn, one of the most remote inhabited islands on Earth, roughly 2,100 kilometers southeast of Tahiti. They were completely isolated. They had no external accountability. They had conflicting interests and a social structure that was never designed to sustain itself over generations. Within a few years, internal violence had killed most of the adult men. The community that survived and eventually stabilized did so through a combination of luck, the specific personalities involved, and the gradual development of new social norms that were adapted to their extreme circumstances. But it was close, very close to complete collapse. Or consider the dynamics observed in Antarctic research stations, which are the closest real-world analog we have to long-duration, isolated habitation. These are small groups, typically between 13 and 100 or so people depending on the station and the season, living in complete physical isolation for months at a time, entirely dependent on each other for survival, operating under formal institutional authority structures imposed from outside before arrival. Researchers studying these communities have documented a consistent pattern of social dynamics, the emergence of informal leadership structures that do not always align with formal ones, the development of intense interpersonal conflicts over seemingly minor issues, the formation of tight cliques and social exclusions, and periodic crises of authority where the formal governance structure comes under genuine stress. And again, These are people who chose to be there, who know exactly when they are leaving, who have continuous communication with the outside world, and whose mission duration is measured in months, not centuries. The governance challenge on a generation ship is not just harder than any of these historical analogies. It is categorically different, because the ship's social contract, set of rules and values and power structures that determine how decisions are made and how resources are allocated and how conflicts are resolved, has to survive not just one administration, not just one generation, but potentially dozens of generational transitions, each one a potential point of rupture, each one a moment where the people currently alive might legitimately ask, why are we bound by decisions made by people who died 100 years before any of us were born? This is actually a question with deep roots in political philosophy. Thomas Jefferson famously argued that constitutions should expire every 19 years, roughly one generation, because the living should not be perpetually governed by the decisions of the dead. He believed that each generation had the right to renegotiate its social contract from scratch. In the context of a generation ship, that idea is either profoundly liberating or catastrophically dangerous, depending on how you look at it. Liberating because it takes seriously the autonomy and agency of the people actually living the mission. Catastrophically dangerous because the mission has physical constraints that cannot be renegotiated by majority vote. The ship needs to keep moving toward its destination. The life support systems need to keep running. The genetic diversity protocols need to be maintained. These are not political preferences, they are survival requirements, and a generation that decides, democratically and in full good faith, to prioritize something else, to redirect resources, to change course, to abandon protocols established by people they never met, could doom every generation that follows them. So how do you design a governance system that is flexible enough to survive centuries of social change, legitimate enough to command genuine buy-in from people who never consented to it, and rigid enough to protect the mission-critical functions that cannot be compromised? Nobody has a fully satisfying answer to this, but researchers have identified several principles that seem important. The first is transparency. Every person born on the ship needs to understand as deeply and as honestly as possible the actual physical and biological situation they are in, not a sanitized or simplified version designed to prevent panic, but the real picture, the radiation environment, the resource constraints, the genetic requirements, the engineering realities, the reasoning behind every major protocol. A society that understands why the rules exist is far more likely to maintain them voluntarily than one that follows them out of habit or authority. The second is adaptability. The governance system cannot be so rigid that it cannot respond to genuinely new circumstances. A mission designed 300 years ago could not possibly have anticipated every situation that arises. The people living the mission need genuine mechanisms for proposing and implementing changes, not just cosmetic changes, but fundamental ones, if circumstances genuinely warrant. The key is distinguishing between the non-negotiable physical constraints of the mission and the negotiable social arrangements built around them. The third is redundancy, not just in engineering systems, but in social ones. Multiple overlapping institutions, multiple independent sources of authority, multiple formal and informal mechanisms for resolving conflicts, so that the failure or corruption of any single system does not bring the whole structure down. The most resilient human societies on Earth are not the ones with the most powerful central authorities. They are the ones with the most robust networks of distributed decision-making and mutual accountability. And the fourth, the one that I think is the most underappreciated and the most difficult to engineer deliberately, is meaning. The people on the ship need to genuinely believe that what they are doing matters. Not just intellectually, not just because they were taught it in school, but in the deep, motivating, identity-forming way that meaning actually functions in human psychology. Viktor Frankl, the psychiatrist and Holocaust survivor who wrote Man's Search for Meaning, observed that the prisoners who survived the Nazi concentration camps, the most extreme conditions of confinement, deprivation, and powerlessness imaginable, were disproportionately those who had a sense of purpose that transcended their immediate circumstances, something they were living for, something that gave the suffering a frame that made it bearable, a generation-ship society that loses its sense of meaning, that stops believing in its collective gut that the journey matters, that the destination is worth it, that their lives inside those walls are part of something larger than themselves, is a society that is already halfway to collapse, regardless of how well its life support systems are functioning. Meaning is not a luxury. On a generation ship, it is as essential as oxygen. How do you build it deliberately? How do you design a culture that sustains meaning across centuries through hardships and failures and generational transitions and the slow erosion of connection to the world that launched the mission in the first place? Through art, almost certainly, through ritual, through the kinds of shared stories and symbols and practices that every human culture has ever developed to bind itself together and remind itself of what it values and why. Through education that does not just transmit information, but transmits passion, the genuine infectious excitement of understanding something true about the universe. And maybe, most importantly, through the ongoing practice of science itself, because science is not just a body of knowledge, it is an attitude, a way of being in the world that is simultaneously humble and ambitious, rigorous and creative, endlessly curious and endlessly willing to be surprised, a culture that practices science, that keeps asking questions about its own situation, keeps measuring and testing and revising its understanding, keeps finding new things to wonder at even within the bounded world of the ship, is a culture that is generating its own meaning continuously, rather than relying on a fixed supply that might eventually run out. The ship itself is a universe in miniature. The ecology of its closed biosphere, the physics of its propulsion system, the biology of its crew, the chemistry of its recycled atmosphere, all of it is endlessly complex, endlessly interesting, endlessly yielding new things to discover for anyone who looks carefully enough. And that inexhaustible complexity is not a bug. It is one of the most powerful arguments for why a generation ship society might be more resilient than the worst-case scenarios suggest. Because as long as there are people on board who are genuinely curious about where they are and what they are doing, the mission has a heartbeat. And that, I think, is something worth holding on to as we go deeper into the most unsettling corner of this entire conversation, because we are going to look at something that the governance question inevitably leads to, something that the history of isolated societies, the psychology of confinement, and the physics of the situation all point toward quietly but insistently. The question of what happens when things go genuinely, catastrophically wrong, not a minor equipment failure, not a social conflict that the governance system manages to resolve, but a civilizational crisis, the kind that on Earth we have sometimes recovered from and sometimes have not, the kind that on a generation ship plays out with no safety net and no second chances. There is a thought experiment that I want you to sit with for a moment. Imagine you are 150 years into the journey. The ship has been traveling for a century and a half. Every single person who was alive at launch is dead. Their children are dead. Their grandchildren are dead. The people alive right now, the ones running the reactors and tending the crops and teaching the children and making the decisions, are 4 or 5 generations removed from anyone who ever stood on the surface of a planet. Whoever felt actual wind? Whoever saw a sky that was not a ceiling, and then something breaks, not something small, not a pipe that needs replacing or a crop yield that comes in lower than expected, something fundamental, something at the level of the ship's core systems. Maybe it is the primary water recycling processor, the machine that takes biological waste and atmospheric moisture and chemical runoff and turns it back into drinkable water. Maybe it is a slow failure in the radiation shielding around the reactor core. Maybe it is a cascade of smaller failures that individually would be manageable, but together create a situation that nobody has the knowledge to fully diagnose, because the engineers who designed these systems have been dead for 100 years, and their documentation, passed down through generations of maintenance crews, has accumulated errors and gaps the way any document does when it is copied and reinterpreted by people working in changing circumstances with incomplete context. Whatever it is serious, and the people facing it have never dealt with anything like it before, because the ship has been running reasonably well for 150 years, and the crisis management protocols that the original designers built into the mission assume a level of technical expertise and institutional knowledge that has, quietly and invisibly, eroded over the generations. This is not a hypothetical designed purely for dramatic effect. It is a real pattern that engineers and systems theorists have identified in complex, long-lived technical systems. It is called knowledge decay, and it is one of the most insidious risks in any system that depends on specialized human expertise maintained over long time periods. We have seen versions of it here on Earth. The techniques used to manufacture certain components of the Saturn V rocket, the vehicle that carried human beings to the moon between 1969 and 1972, were so specialized and so dependent on the tacit knowledge of individual engineers and craftspeople that when NASA tried to recreate them decades later, they discovered that the knowledge had simply not been fully captured in documentation. The people who knew how to do certain things were gone, and what they knew had gone with them. NASA eventually had to develop entirely new manufacturing processes to produce components that performed equivalently, because recreating the originals was no longer possible, and the Saturn V program lasted about a decade. We are talking about a generation ship mission lasting centuries. The sociologist Charles Perrow wrote a deeply influential book called Normal Accidents, published in 1984, in which he argued that in sufficiently complex, tightly coupled systems where many components interact in non-linear ways, and where failures in one part can rapidly cascade into failures in others, accidents are not the result of individual errors or bad luck. They are an inevitable emergent property of the system's structure. They are, in his term, normal, expected. Built into the architecture of the thing itself, a generation ship is perhaps the most complex, most tightly coupled system ever conceived. Every subsystem depends on every other subsystem. The life support depends on the power system, depends on the reactor, depends on the cooling system, depends on the water recycling, depends on the agricultural system, depends on the crew's health, depends on the medical system, depends on the pharmaceutical manufacturing, depends on the chemical processing, depends on the water recycling. Everything is connected to everything else, and the failure modes multiply with every connection. Perrow's framework was developed in the context of nuclear power plants, chemical factories, and air traffic control systems. Systems that are complex but are also continuously maintained by large external organizations with access to replacement parts, specialist expertise from outside, and the ability to shut the system down in an emergency. None of those safety nets exist on an interstellar vessel, so what do? How do you design a system that is genuinely resilient against the kind of cascading failure that Perrow's framework predicts is essentially inevitable over a long enough time frame. The most honest answer is that you probably cannot make it completely resilient. Not against everything. The best you can do is a combination of approaches, none of which is sufficient on its own, but which together might be enough. Radical redundancy is the first. Not just backup systems, but backups of the backups, designed by different engineering teams using different principles, so that a systemic flaw in one design does not propagate through all its copies. The more diverse the redundancy, the more failure modes it covers. Modularity is the second, designing the ship so that different sections can be isolated from each other, so that a failure in one module does not automatically cascade into the others. This is already standard practice in spacecraft design. The International Space Station, for example, is divided into modules that can be sealed off from each other in an emergency. Scaling this principle up to a vessel designed for centuries of autonomous operation, with the ability to physically separate and reconnect sections as needed, is a much harder engineering problem, but the same fundamental logic applies. The third is what systems theorists call graceful degradation, designing systems so that when they fail slowly and partially rather than catastrophically and completely. A water recycling system that loses efficiency gradually, giving the crew months to diagnose and address the problem, is far preferable to one that works perfectly right up until the moment it stops working entirely. Building in early warning indicators, designing for partial functionality under stress, creating systems that degrade in predictable and manageable ways. All of this is part of what makes the difference between a failure that a crew can adapt to and one that kills everyone before they know it is happening. But here is the thing. Even with all of that, even with the best possible engineering, the most sophisticated redundancy, the most carefully designed graceful degradation, there will be scenarios that nobody anticipated. Because the universe is more creative than any engineering team. Because a journey of centuries in the interstellar medium will present conditions and challenges that no simulation running on Earth fully captured. Because human beings, living under extraordinary pressure in extreme circumstances for multiple generations, will make decisions and take actions that no designer predicted, and some of those unanticipated scenarios will be survivable. The crew will improvise, adapt, solve the problem in ways nobody planned for, and the mission will continue. Human ingenuity under pressure is genuinely remarkable. The history of spaceflight alone contains dozens of examples, where Apollo 13 being the most famous, where a catastrophic oxygen tank explosion on the way to the moon was somehow transformed, through improvisation and brilliance under pressure, into a successful emergency return to Earth. The crew of Skylab in 1973 improvised a makeshift sunshade from a parachute and a couple of tent poles when the station's thermal protection was damaged during launch, saving a mission that otherwise would have been abandoned. But some unanticipated scenarios will not be survivable. Some failures will be too fast, too total, too far beyond the crew's ability to respond. And on a generation ship traveling between stars, those scenarios end not just the mission but every life aboard, potentially thousands of people. The accumulated knowledge and culture and relationships of generations, gone in whatever amount of time it takes for the atmosphere to vent, or the reactor to fail, or the food system to collapse beyond recovery. This is the shadow that sits underneath every optimistic discussion of interstellar travel. Not the solvable problems, the radiation, the genetics, the propulsion, the governance. As hard as those are, they are at least theoretically addressable with sufficient ingenuity and resources. It is the unknowable problems, the ones that will not reveal themselves until they are already happening, in a place where there is no help coming and no second chances, And I think it is important to sit with that shadow honestly rather than dismissing it or papering over it with optimism. Because the people who would actually make the decision to launch a generation ship, the scientists and engineers and ethicists and policymakers who would have to look at the full picture and decide whether the mission is justified, need to carry that shadow with them. They need to feel its weight. They need to have genuinely wrestled with what it means to knowingly send thousands of human beings into a situation where catastrophic, total, irreversible failure is a real possibility, not a near certainty. Let me be clear about that. The engineering challenges of a generation ship are immense, but they are not magic. A sufficiently advanced civilization, one perhaps a century or two further along the technological curve than we are today, might be able to address the known failure modes with a degree of reliability that makes the mission genuinely reasonable rather than reckless. We should not assume that because we cannot solve these problems today, they will never be solvable. That assumption has been wrong every time humanity has made it about any major technological challenge. But reasonable is not the same as certain, and the gap between reasonable and certain is filled with people, with lives, with generations of human beings who will exist inside those walls and have no say in the risks that were accepted on their behalf before they were born. There is a concept in ethics called the precautionary principle, roughly the idea that when an action carries the risk of serious or irreversible harm, the burden of proof lies with those who want to take the action rather than those who oppose it. It is a principle with real practical value, particularly for technologies whose failure modes are poorly understood. But it is also a principle that, taken to its extreme, would have prevented almost every significant human advance, because almost every significant human advance has carried some risk of serious harm. The generation ship sits right at the intersection of these competing ethical imperatives. The risk of not going, of keeping all of humanity's eggs in one planetary basket indefinitely, is real and serious and grows more serious with every century that passes. The risk of going, of accepting all the known and unknown failure modes of a centuries-long interstellar mission, is also real and serious and falls on people who cannot speak for themselves because they do not yet exist. There is no clean resolution to this tension. There is only the ongoing, honest, uncomfortable work of thinking it through as carefully as we can, with as much scientific knowledge as we can bring to bear, and as much genuine humility about the limits of our foresight as we can muster. And there is one more dimension of this that we have not yet fully explored, one that connects the generation ship to something happening right now in our own civilization, in ways that feel closer and more urgent than anything involving spacecraft and distant stars. Something that the generation ship forces us to confront because it strips away all the comfortable distractions and leaves the question completely bare. What are we actually for? Not as individuals, as a species, as this particular arrangement of matter that has been stumbling and striving and building and destroying and creating and discovering for 300,000 years on the surface of a small rocky planet. What is the point of all of it? What are we trying to accomplish? What do we owe each other? And what do we owe the future? And what does it mean to live well given everything we know about how large the universe is and how small we are and how uncertain our continued existence actually is? The generation ship does not answer these questions, but it asks them with unusual clarity, because when you are designing a vessel that has to sustain human civilization across centuries of isolation, you cannot avoid them. You have to decide what to bring, what to preserve, what values to build into the foundation of the society you are launching, what version of humanity you are trying to carry across the dark. And those decisions about what matters, about what is worth preserving, about what we are ultimately for, are not just decisions for a future generation ship crew to make. They are decisions that every generation has to make, here and now, on this planet, in the choices we make about what we build and what we protect and what we pass on to the people who come after us. The generation ship is a mirror, and what it shows us, when we look into it honestly, is a version of the question we are always already asking, whether we know it or not. How do we keep going? How do we make it worth it? How do we carry the best of what we are into whatever comes next? There is something quietly extraordinary happening right now in laboratories and observatories and research institutions scattered across the planet that most people never hear about, not because it is secret, not because the people doing it are trying to hide it, but because the timescales involved are so long and the goals so distant that it does not fit neatly into the news cycle, into the quarterly earnings report, into the political calendar. It does not produce a dramatic headline every few months. It produces instead something slower and more durable, a gradual accumulation of understanding that is, piece by piece, making the impossible slightly less impossible. Let us start with the telescopes, because before you can seriously plan a mission to another star system, you need to know what you are aiming at. And the transformation in our ability to characterize other worlds over just the last decade has been nothing short of revolutionary. The James Webb Space Telescope, which we have mentioned several times already, is the centerpiece of this revolution. But it is worth spending a moment really appreciating what it represents as an engineering and scientific achievement, because I think it tends to get discussed in ways that understate how remarkable it actually is. Webb was launched on December 25, 2021, after decades of development, cost overruns, technical setbacks, and delays that at various points seemed like they might kill the project entirely. It was folded up inside the Ariane 5 rocket that carried it to space, its primary mirror, 6.5 meters across, and composed of 18 individually adjustable gold-coated beryllium hexagonal segments, had to be folded origami style to fit inside the fairing. Over the following weeks, it unfolded itself in space, in a sequence of deployments so complex and so dependent on every single step going correctly that NASA engineers described the launch period as 29 days of terror. It went perfectly, every hinge, every latch, every motor performed exactly as designed. Webb reached its operational position at the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth in the direction away from the Sun, and began its science operations in the summer of 2022. And what it has shown us since has fundamentally changed our picture of the universe beyond the exoplanet atmospheric characterization we discussed earlier. Webb has peered deeper into the early universe than any instrument before it, observing galaxies that formed within just a few 100 million years of the Big Bang, and forcing cosmologists to revise their models of how quickly structure formed in the early universe. It has revealed details of star-forming regions in our own galaxy with unprecedented clarity, showing us the chaotic, violent, extraordinarily beautiful process by which clouds of gas and dust collapse under gravity and ignite into nuclear furnaces. It has detected complex organic molecules, the chemical building blocks of life as we know it, in the disks of material surrounding young stars, suggesting that the chemistry of life may be seeded into planetary systems almost from the moment they begin to form. Every one of these discoveries matters for the generation ship question. The deeper we understand the universe, the better we characterize the planets we might one day aim for, the more precisely we understand the radiation environment of interstellar space, the more accurately we can model the star systems we might visit, the better positioned we are to make informed decisions about if, when, and how to attempt the crossing. And Webb is not the end of this story. It is closer to the beginning. The extremely large telescope being built by the European Southern Observatory on Cerro Armazones in Chile's Atacama Desert, a site chosen for its extraordinary atmospheric clarity and the sheer number of clear nights per year, will, when it achieves first light, be the largest optical telescope ever built. Its primary mirror, 39 meters across, will collect so much light that it will be able to directly image Earth-sized planets around nearby stars and spectroscopically analyze their atmospheres in ways that are currently beyond any existing instrument. The ability to look at a planet circling Alpha Centauri or Barnard's star or any of the dozens of stellar systems within 20 light-years of Earth and read the composition of its air to detect oxygen, methane, water vapor, carbon dioxide, and the specific combinations of molecules that would indicate biological activity is not a fantasy. It is an engineering project currently under construction. There is also NASA's proposed Habitable Worlds Observatory, a next-generation space telescope concept that has been identified as a high priority in the most recent decadal survey of astronomy, the process by which the scientific community collectively decides what its most important goals and instruments are for the coming decade. The Habitable Worlds Observatory is specifically designed to search for biosignatures on Earth-like planets around Sun-like stars. It does not yet have a confirmed budget or launch date, but the scientific community's prioritization of it signals something important. The question of whether other worlds harbor life has moved from the margins of astronomy to its very center. It is no longer a niche interest. It is a mainstream scientific priority with institutional support and a realistic development pathway. Now, let us talk about propulsion, because this is where the gap between where we are and where we need to be is widest, and where the real work is perhaps the most fascinating. The most credible near-term research program, specifically aimed at interstellar propulsion, is Breakthrough Starshot, which we touched on earlier. But it is worth going deeper into what the actual technical challenges are, because they reveal just how hard the problem is even for gram-scale probes, let alone crewed vessels. The Starshot concept involves using a ground-based laser array, potentially gigawatts of coherent laser power focused on a tiny, ultra-thin light sail to accelerate a microchip-scale spacecraft to 20% of the speed of light over the course of a few minutes. The physics work. Light does exert pressure, and a sufficiently thin, reflective sail with a sufficiently small mass can in principle be accelerated to significant fractions of the speed of light by a powerful enough laser. But the engineering challenges are extraordinary. The sail material needs to be extraordinarily thin. We are talking about films just a few hundred atoms thick, while being highly reflective at the laser wavelength, thermally stable enough not to vaporize under the intense illumination, and structurally coherent enough to maintain its shape during acceleration. Researchers have been experimenting with graphene and other two-dimensional materials as potential candidates. Progress has been real but incremental. The laser array itself presents a different set of challenges. To generate the required power levels, you would need an array of individually modest lasers, perhaps on the order of 100 million separate laser emitters, all phase-locked so that they act as a single coherent beam. The technology for phase-locking large numbers of lasers exists in principle, but has never been demonstrated at anything close to the scale required. And you would need to track the accelerating sail with this beam for the full duration of the acceleration phase, minutes during which the target is moving at a significant fraction of the speed of light, and the beam divergence over even short distances becomes a significant engineering problem. Then there is the communication problem. A probe traveling to Alpha Centauri at 20% of the speed of light would reach the system in about 20 years. But its transmitter, to send data back across 4.37 light-years, needs to be extraordinarily powerful relative to its gram-scale mass. The signal would take another 4.37 years to return. We would receive the first data from another star system roughly 24 years after launch. That is actually not that long in scientific terms. 24 years is within a human career. It is an achievable goal, but what about crewed missions? The energy requirements, as we discussed before, are almost incomprehensible with current technology. What is actually being done to address them? Several research programs around the world are quietly making progress on components of the problem. At the University of Alabama in Huntsville, researchers have been working on plasma propulsion systems that, while nowhere near interstellar capability, are pushing the boundaries of what ion drives can achieve. The Dawn spacecraft, which used ion propulsion to visit both the asteroid Vesta and the dwarf planet Ceres, demonstrated the real-world capability of these systems in deep space operations. The Hayabusa 2 mission, operated by the Japan Aerospace Exploration Agency, used iongens to rendezvous with the asteroid Ryugu, collect samples and return them to Earth. A mission profile that required extraordinarily precise, long-duration propulsion management. These are baby steps in the context of interstellar travel, but they are real steps, generating real engineering knowledge about how to operate propulsion systems in deep space over extended periods. Every mission teaches us something. On the fusion side, the propulsion concept that most researchers consider the most realistic pathway to the velocities needed for even a slow interstellar mission, the progress over the last decade has been genuinely exciting, even if it remains some distance from practical application. The private fusion sector has attracted billions of dollars in investment and gathered some of the most talented physicists and engineers in the world. Commonwealth Fusion Systems, a spin-out from MIT, has demonstrated record-breaking magnetic field strengths using high-temperature superconducting magnets, a technology that significantly changes the engineering calculus for compact fusion reactors. Helion Energy has received substantial investment and set a target of demonstrating net electricity from fusion by the end of this decade. TA Technologies is pursuing a fundamentally different approach using a field-reversed configuration plasma. None of these companies are building spacecraft engines, but the underlying physics of fusion, the conditions under which light nuclei can be forced to combine and release energy, is the same whether you are building a power plant or a propulsion system. Progress on one informs the other, and there is something happening in the closed ecosystem research space that is equally important, even if it attracts far less attention. Because propulsion gets you to the destination, but it is life support that keeps you alive long enough to get there. And the Biosphere 2 experiment, as we discussed at the very beginning of this series, demonstrated just how badly we can fail at this even under ideal conditions. The successor to Biosphere 2, in scientific terms, is a collection of research programs studying closed-loop life support in smaller and more controlled ways. The MELISSA project, the acronym stands for Microecological Life Support System Alternative, is a European Space Agency initiative that has been running since 1989 at a facility in Barcelona, Spain. It is designed to develop a completely closed regenerative life support system capable of recycling all biological waste into food, water and oxygen using a combination of microorganisms, algae, higher plants and fish. It is a genuine, ongoing attempt to solve exactly the problem that Biosphere 2 failed to solve, but approached with far more scientific rigor and far less ambition about scale, working through the system component by component rather than trying to recreate a full biosphere at once. The MELISSA loop is not yet complete. There are still components that have not been fully integrated with the rest of the system. But the decades of research it has generated have produced a detailed understanding of the microbial ecology of closed systems, the nutrient cycling requirements of a human-sustaining biosphere, and the failure modes that need to be designed against, knowledge that did not exist when Biosphere 2 was built, and that would be absolutely essential for any serious generation ship life support system. Meanwhile, NASA's Advanced Life Support Program has been developing and testing individual components of closed-loop life support for use on the International Space Station and future long-duration missions. The environmental control and life support system aboard the station already recovers about 93% of the water from crew perspiration, respiration, and urine through a combination of distillation, filtration, and chemical processing. That sounds impressive, and it is a genuine engineering achievement, but for a generation ship, 93% recovery would mean accumulating a catastrophic deficit over centuries. You need something close to 100%, and closing that last 7% turns out to be extraordinarily difficult because the contaminants in the remaining fraction are diverse, chemically complex, and resistant to the relatively simple treatment processes that handle the bulk of the water recovery. The research programs working on this gap are small, underfunded, and largely invisible to the general public. But they are real, and they are making progress, and that progress is not just relevant to interstellar travel. It is directly relevant to human settlements on the Moon and Mars, which are much nearer-term goals that face similar life support challenges on shorter timescales. The work that closes the gap for a Mars base is the same work that makes a generation ship more viable. The problems are not separate, they are the same problem at different scales. There is also a growing body of research on the psychological and social dimensions of long-duration spaceflight that we would be remiss not to mention. The Human Research Program at NASA has been systematically studying the behavioral health and performance of astronauts on long-duration missions, identifying the factors that predict good versus poor psychological outcomes, developing countermeasures for cognitive and emotional degradation, and building the evidence base for what a genuinely human-centered approach to long-duration spaceflight would look like. The HERA project, the Human Exploration Research Analog, runs missions in a simulated deep space habitat at the Johnson Space Center in Houston, studying how small crews perform under mission-relevant conditions over extended periods. The Mars 500 study, conducted between 2010 and 2011, isolated 6 volunteers in a simulated spacecraft in Moscow for 520 days, roughly the duration of a round trip to Mars, and monitored their physical and psychological health throughout. The results were nuanced. Physical health was generally maintained, psychological health was more complicated. Sedentary behavior increased dramatically over the course of the mission. Sleep disturbances were common. Some crew members showed signs of significant psychological withdrawal in the later stages. The mission demonstrated both that humans can endure very long periods of isolation and confinement without complete psychological breakdown, and that the cost of doing so is real and needs to be taken seriously in mission design. 520 days. A generation ship mission to even the nearest star would last tens of thousands of times longer. The extrapolation from 500 days to 50,000 years is not linear. It involves qualitative changes in the human experience that no short-duration analog study can fully capture. But the research is building the foundation of understanding that a more complete picture will eventually require. What strikes me, looking across all of this research, the telescopes and the propulsion concepts and the closed ecology programs and the psychological studies, is how genuinely, seriously, and quietly the scientific community has been working on these problems for decades. Not with the fanfare of a rocket launch or the dramatic announcement of a new mission, but steadily, methodically, building knowledge that accumulates and compounds over time the way all good science does. We are not close to being ready to launch a generation ship. Let me be absolutely clear about that. The gap between where we are today and where we would need to be is enormous, measured in decades of scientific progress at minimum, and probably in centuries. But the direction of travel is not ambiguous. We are moving toward this, slowly, haltingly, with many false starts and dead ends and budget cuts and political obstacles. But moving, and there is something about that trajectory, about the image of human beings quietly, persistently working on one of the hardest problems ever conceived, across generations, building on each other's work, passing the torch forward. That feels, to me, like exactly the spirit that a generation ship would require. The willingness to work on something whose completion you will not live to see. The capacity to find meaning in contributing to a project larger than your own lifetime. In a way, the generation ship already exists, not as a vessel, as a collective human project, as the slow accumulation of knowledge and capability that might one day make the physical vessel possible. And every scientist who has ever studied an exoplanet atmosphere, every engineer who has ever worked on a closed-loop life support system, every psychologist who has ever run an isolation study, every physicist who has ever pushed the boundaries of fusion research, all of them are in some sense crew. I want to tell you about a photograph. It was taken on February 14th, 1990, by the Voyager 1 spacecraft. At that point, Voyager 1 was approximately 6 billion kilometers from Earth, further from us than any human-made object had ever been. The cameras were about to be shut down permanently to conserve power for the long journey ahead. And before they went dark, the mission team at NASA, led by Carl Sagan, who had been pushing for this image for years against significant institutional resistance, pointed the cameras back toward the inner solar system and took one final series of photographs. In one of those photographs, Earth appears. It is not impressive. It is a tiny point of light, less than a single pixel in size, caught in scattered rays of sunlight that streak across the image like lens flare. You would almost miss it if you did not know where to look. The pale blue dot, Sagan wrote about this photograph in a way that has never been improved upon. He wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." I bring up this photograph and this passage not for sentiment, though the sentiment is entirely warranted. I bring it up because it is directly, structurally relevant to what a generation ship would do to human consciousness, to the way people see themselves and their civilization and their place in the universe. Every human being who has ever lived has had, as the backdrop of their psychological world, a planetary surface, horizon lines, sky, the sense of being embedded in something enormous, something that extends in every direction beyond the limits of perception. Even people who have spent their entire lives in cities surrounded by concrete and glass and artificial light carry in their nervous systems the evolutionary inheritance of a species that spent hundreds of thousands of years reading landscapes, tracking weather, navigating by stars. Our sense of scale is calibrated by the world that made us, The people born on a generation ship will not have this. Their psychological world will be bounded not by a horizon but by a wall, not by a sky but by a ceiling, not by the organic, complex, endlessly varied sensory richness of a planetary surface, but by the engineered, maintained, ultimately artificial environment of a vessel built by human hands. Whatever biospheric spaces the ship contains, whatever parks or gardens or growing areas the designers have managed to create, they will be legible as constructed, as contained, as human-made in a way that a forest or an ocean or a mountain range is not. What does that do to a person? What does it do to a culture? When there is no outside, when the boundary of the world is also the boundary of the machine keeping you alive, how does that shape the way people think about themselves and their place in things? We genuinely do not know. There is no historical precedent for it. We can look at analogies, at island cultures that developed in relative isolation, at communities that have lived for generations in extreme environments, at the psychological research on confined populations, but none of these are the real thing. None of them involve people who have never, not once in their lives or in any living memory, stood on open ground under an open sky. Some researchers speculate that the effect would be profoundly constraining, that the absence of horizon, of the sense of infinite extension that a planetary surface provides, would produce a kind of psychological claustrophobia that becomes cultural over generations, a worldview that is inherently bounded, inherently focused on the immediate and the local, inherently suspicious of the abstract and the distant. A culture that loses over time the capacity to think in the large scales that the mission itself requires. Others speculate almost the opposite, that a culture formed in a vessel traveling between stars, a culture that grows up knowing, in a visceral and unavoidable way, that it is crossing an incomprehensible void, that the nearest star is years of travel away, that the universe outside the hull is ancient and enormous and indifferent, might develop a relationship to cosmic scale that is actually deeper and more intuitive than anything available to people living on a planetary surface, where the vast majority of your daily experience has nothing to do with the universe's actual scale, that the generation ship, paradoxically, might produce the most cosmically aware human culture in history, a people for whom the size of the universe is not an abstract fact learned from a textbook, but a lived, felt daily reality. I find myself drawn to something between these two possibilities, something that feels true to what we know about human psychology and human culture more generally, which is that people make meaning from whatever materials they have, that the capacity for wonder, for curiosity, for the sense of the sublime, the feeling of being in the presence of something so large and so complex that it exceeds your ability to fully comprehend it, is not dependent on any particular external environment. It is a property of human consciousness. It can be activated by a mountain range, or by a mathematical proof, or by a piece of music, or by the night sky, or by the realization of what is happening at the molecular level inside a living cell. A culture on a generation ship would find its sources of the sublime in different places than we find ours, but it would find them, because the need for the sublime, the need to reach beyond the ordinary and touch something larger, is not culturally learned. It is built into the architecture of what we are. It is one of the things that makes us recognizably human across every culture and every era of our history. And there is something specific to the generation ship situation that I think could become a uniquely powerful source of meaning if the culture develops in the right way. Something that is available to these people and not quite available to us in the same form. The stars not as lights in a sky, not as distant, abstract points that we know intellectually are suns but that feel, emotionally, like decorations, but as destinations, as the actual physical reality around which the entire civilization is organized. Imagine growing up in a culture where the star you are traveling toward is not a mythological concept or an astronomical fact, but a practical reality, something that is getting infinitesimally but genuinely closer every day, something that your grandparents were slightly further from than you are, something that your grandchildren will be slightly closer to, where the journey is not a metaphor but the actual condition of your existence, where the night sky, seen through whatever observation ports or screens or virtual environments the ship provides, is not just beautiful but personal. These are the stars among which your people are traveling. That one, slightly brighter than it was in the records from a century ago, is where you are going. I think that could produce a relationship to the cosmos that is unlike anything human beings have experienced before. A sense of genuine participation in the universe's story rather than passive observation of it. Not the pale blue dot seen from 6 billion kilometers away, the sense of how small and fragile we are, but something complementary to that, the sense of being genuinely out there, of being not just observers of the cosmic scale, but travelers within it. Carl Sagan also wrote something else that I think about often in the context of this conversation. He wrote, "We are a way for the cosmos to know itself." That idea, that consciousness is not separate from the universe, but is the universe doing something extraordinary with a small fraction of its matter, turning it back on itself in self-examination, is one of the most beautiful and, I think, one of the most accurate things ever said about the human situation. We are made of the same atoms as the stars. We are continuous with the physical universe. And when we look up and ask questions about what is out there and how it works and whether we are alone, we are not standing outside the universe looking in. We are inside it, looking around. A generation ship is the most literal possible expression of that idea. It is the cosmos, in the form of a small community of conscious beings, deliberately choosing to know itself better by traveling to a part of itself that it has not yet reached. It is curiosity given a hull and a propulsion system. It is wonder made navigable. And here is where I want to bring something into focus that has been implicit throughout this entire series, but that I have not said directly. The reason the generation ship is terrifying, and it is genuinely terrifying for all the reasons we have spent 14 parts exploring, is not separate from the reason it is magnificent. They are the same reason. It is terrifying because the stakes are so high, because the universe does not care whether we make it, because the void between stars is genuinely, incomprehensibly vast and genuinely, mercilessly hostile to the kind of complex, fragile, water-based chemistry that produces beings capable of asking questions about it. Because failure, in this context, is absolute and irreversible. But those are also exactly the conditions that make the attempt meaningful. We are not awed by things that are easy. We are not moved by stories of comfortable, safe, guaranteed success. The things that reach into us and change something, the achievements and the attempts that we carry with us and that carry us forward, are the ones where the difficulty was real, where the cost was real, where the possibility of failure was real, and where something chose to try anyway, not out of recklessness, not out of ignorance of the risks, but in full knowledge of them and with a sense of purpose larger than the fear. That is the generation ship. That is what it is. At its best, in the version of the future where we have thought about it carefully enough and built it wisely enough and populated it with people who understand what they are part of. It is the most deliberate, the most expensive, the most dangerous, and the most profound act of curiosity in human history. It is the moment when a species that evolved on one small world says, we want to know what is out there, not just through our instruments, not just through our mathematics. We want to go and see. There is a word in Portuguese a language with a particular genius for naming emotional states that other languages leave unnamed, that I think captures something essential about this. The word is saudade. It refers to a deep, bittersweet longing for something beloved that is absent, something cherished that you cannot reach. It is often described as a specifically Portuguese feeling, though anyone who has ever missed something they loved deeply knows exactly what it points to. I think saudade is part of what drives the generation ship impulse, part of what drives all exploration, all science, all the reaching outward that our species cannot seem to stop doing, even when it would be safer and easier to stay home. There is something out there that we have not seen yet, something we do not know yet, and the not knowing creates a longing that is, in its way, as real as hunger, as intestine thirst. The generation ship is humanity's answer to that longing taken to its logical extreme. It is saudade given a destination and a departure date, and whether that answer is wise, whether the cost is worth it, whether the attempt is justified, whether we will do it well enough to actually get there, those are questions that we cannot answer yet. They belong to the future, to the people who will have access to technologies and knowledge and wisdom that we do not yet possess, to generations not yet born who will look back at us the way we look back at the first hominids who crossed a land bridge into an unknown continent, and who will understand things about the universe and about themselves that we can barely imagine. What we can do, what we are doing right now in this conversation, is take the question seriously, to sit with the full weight of it rather than reducing it to either naive optimism or dismissive pessimism, to hold the terror and the wonder together, which is the only honest way to hold them. Because the universe is not optimistic and it is not pessimistic, it is vast and it is ancient, and it operates according to laws that do not bend for us, and inside that vastness and that antiquity, on a small rocky planet in an unremarkable region of a spiral galaxy, something happened that has not, as far as we know, happened anywhere else in the observable universe. Matter organized itself into beings who could look up and ask why, who could imagine crossing the void, who could build the mathematics to describe the shape of space-time and the engineering to leave their home world and the philosophy to ask whether they should. That is the most extraordinary thing in the universe that we know about, and the generation ship is, in a real sense, that extraordinary thing deciding to introduce itself to the rest of the cosmos. There is a question that has been sitting underneath everything we have discussed in this series, patient and quiet, waiting for us to finally turn and look at it directly. We have circled it from every angle. We have approached it through physics and biology, and ethics and psychology, and history and philosophy. And now at the end, I want to ask it plainly. What kind of people would we need to be? Not what kind of technology, not what kind of propulsion system or life support architecture or governance structure. Those matter enormously, and we have spent a great deal of time on them, and they will be the work of generations of scientists and engineers who are probably not yet born. But underneath all of it, prior to all of it, is the human question, the character question, the question of what values and capacities and ways of being in the world a civilization would need to have developed before it could responsibly attempt something like this. Because here is the thing that I keep coming back to after everything we have explored. The generation ship is not primarily an engineering problem. It is a wisdom problem. The engineering is hard, extraordinarily hard, perhaps the hardest engineering challenge our species has ever set itself. But engineering problems, given sufficient time and resources and intelligence, tend to get solved. Human beings are extraordinarily good at solving engineering problems. The history of technology is a history of things that seemed impossible becoming routine with enough focused effort. Wisdom is different. Wisdom does not scale the way engineering scales. It does not accumulate automatically with time. Civilizations can become enormously more technologically capable without becoming meaningfully wiser, and the history of our species contains more than enough examples of technological capability deployed without sufficient wisdom, producing outcomes that were catastrophic precisely because the power available exceeded the judgment being used to wield it. A generation ship in the hands of a civilization that has not developed the wisdom to use it well is not an inspiring story about human potential. It is a tragedy waiting to happen. Thousands of lives, and the generations that would have descended from them, committed to a journey that ends in failure, because the people who launched it had not yet learned what they needed to learn. So what does the wisdom look like? What are the actual characteristics, not the abstract virtues, but the specific, practical, cultivated capacities that a generation ship civilization would need to have? The first is the ability to think across time. Genuinely, not just rhetorically, human beings are not naturally good at this. We are wired by evolution for the immediate, for the threat that is present right now, the resource that is available today, the relationship in front of us, the psychological research on temporal discounting, the tendency to value present outcomes more than future ones, even when the future outcomes are objectively larger, is robust and consistent across cultures. We systematically underweight the future. We systematically overweight the present. And for almost all of human history, this was not a catastrophic flaw. The future was genuinely uncertain, and the present was genuinely urgent, and prioritizing immediate survival over long-term planning was usually the right call. But a generation ship runs on a timescale where decisions made today will have consequences for people who are not yet born, and who will themselves make decisions whose consequences will fall on people not yet born from their perspective. Every significant choice aboard is, in some sense, a choice about the future rather than the present. The food supply management, the genetic protocols, the resource allocation, the maintenance schedules, the educational system, the governance structure, all of it is oriented toward outcomes that are decades or centuries away. A culture that cannot think on those timescales cannot manage those systems well. It will consistently sacrifice the long term for the short term, the way that organisms, companies, and civilizations so often do when the incentives are not carefully designed. Developing the genuine, practiced capacity to think across generations, not as an intellectual exercise but as a lived cultural habit, is one of the most important things a generation ship civilization would need, and it is also, not coincidentally, one of the most important things that our civilization needs right now on Earth for reasons that have nothing to do with interstellar travel, climate change, biodiversity loss, long-term debt, nuclear waste storage, pension systems. Every major challenge of the 21st century has this structure, costs and consequences that are distributed across time in ways that our natural psychological wiring does not handle well. The generation ship is not a unique case. It is an extreme version of a general problem we are already failing to solve. The second capacity is the ability to cooperate at scale without requiring a common enemy. This sounds simple. It is not. The history of large-scale human cooperation is, with remarkably few exceptions, a history of cooperation organized around a shared threat. Nations unite against external enemies. Communities mobilize against natural disasters. Institutions cohere around existential challenges. The cooperation is real, and it is often extraordinary. Human beings are capable of remarkable feats of collective action when sufficiently motivated, but the motivation tends to require a clear, present, and identifiable danger, something to be against. A generation ship in the middle of the interstellar void, a century into its journey, with the launch world a tiny, unreachable point of light far behind, and the destination still generations away does not have a clear and present external threat. The threats are real, the radiation, the system failures, the resource constraints, but they are diffuse and slow and technical rather than dramatic and immediate. They are the kind of threats that require sustained, boring, unglamorous attention rather than heroic mobilization, and sustaining that kind of attention in a community of thousands of people over centuries, without the psychological fuel of an external enemy, without the binding power of shared crisis, that requires a form of social cohesion that human beings have very rarely achieved and never maintained indefinitely. The closest examples we have are the great scientific and religious institutions of human history, bodies that have maintained coherent purpose across centuries, not through military force or political coercion, but through shared meaning. The Catholic Church, whatever its many profound failures, has maintained organizational continuity for roughly 2,000 years. Universities like Bologna and Oxford have been operating continuously for nearly 1,000 years. Scientific institutions like the Royal Society, founded in 1660, have maintained a continuous commitment to the values of empirical inquiry across centuries of political, social, and intellectual upheaval. What these institutions share, what makes them useful models, even imperfect ones, is that they found ways to embed their core purpose in culture and ritual and practice, in ways that are transmitted across generations not just as information, but as identity. You do not just learn that you are a member of these institutions, you become a member. The membership shapes how you see yourself, what you value, how you interpret your experience. And that identity, that sense of belonging to something with a history and a purpose larger than your individual life, is a genuinely powerful source of the sustained cooperation that a generation ship would require. The third capacity, and this is the one I want to spend the most time on because I think it is the most counterintuitive, is the ability to be genuinely, radically practiced in disagreement. This might seem like the opposite of what you want in a closed, high-stakes, interdependent community. If everyone needs to cooperate to survive, surely you want alignment rather than disagreement, consensus rather than conflict, a clear set of shared values and a strong central authority to enforce them. But the history of isolated, high-stakes communities that tried to achieve survival through enforced consensus is not encouraging. What tends to happen is that the suppression of disagreement, even when well-intentioned, even when the disagreement being suppressed is genuinely dangerous, produces a brittleness that is worse, in the long run, than the conflicts it prevents. Mistakes go unchallenged, bad decisions accumulate. The feedback loops that would normally correct errors are interrupted, and when the accumulated errors finally become impossible to ignore, the result is not manageable disagreement but crisis, precisely because the mechanisms for handling disagreement were never developed. The most resilient systems in engineering, in ecology, and in human societies are not the most rigid ones. They are the ones that have built-in mechanisms for self-correction, for detecting errors and adjusting, for allowing genuine challenge to established ways of doing things in controlled and constructive ways, without that challenge tipping over into destabilizing conflict. What this requires, at the cultural level, is a sophisticated and practiced relationship to disagreement, not the absence of conflict, but the capacity to engage with conflict in ways that are productive rather than destructive, to disagree without threatening, to challenge without fragmenting, to change course when evidence demands it without treating the change as a defeat, to hold strong views loosely enough to revise them when the situation calls for it. This is, in a deep sense, the attitude of science. Science is not a body of facts. It is a set of practices for managing disagreement, for taking conflicting claims about the world seriously testing them against evidence and updating beliefs accordingly. A scientific culture is one that has internalized the uncomfortable truth that current understanding is always provisional, always subject to revision, always potentially wrong in ways that are not yet apparent, and that this provisionality is not a weakness, but the source of its extraordinary power, because it means the system keeps correcting itself, it keeps getting closer to the truth. A generation ship culture built on genuinely scientific values, not just in its technical practices, but in its social and political ones, would be a culture that handles disagreement well by design, that treats challenges to established practice as valuable rather than threatening, that rewards the person who identifies a flaw in the current approach rather than punishing them for disrupting consensus, that builds in mechanisms for genuine accountability at every level of its governance structure, because it understands that unchallenged power in a closed system is one of the most dangerous failure modes imaginable. The fourth capacity, the last one I want to name, though it is far from the last that matters, is perhaps the simplest to state and the hardest to actually develop. It is gratitude, not gratitude in the performative, socially expected sense. Genuine, deep, practiced gratitude for the extraordinary improbability of being alive at all, of being conscious at all, of being the kind of being that can ask questions about the universe and feel moved by the answers. In a universe that is mostly vacuum and radiation and cold and silence, the fact that there is anywhere at all where complex chemistry has organized itself into something that can love and grieve and wonder and create, that is not something to take for granted. That is the most astonishing fact in all of physics. The people on a generation ship will face hardship that most of us cannot imagine. They will live constrained, difficult, uncertain lives in conditions that are genuinely hostile to human flourishing in many ways. And they will do this not because they chose to be born there. They did not, but because they were, and because the mission is what it is, and because there is no alternative that does not involve abandoning everything their civilization has worked toward. The only thing that makes that livable, the only thing that makes it more than endurance, that elevates it from suffering to meaning, is the capacity to see, within those constraints, what is genuinely extraordinary about their situation, to feel the weight and the wonder of being the first human beings in history to cross the interstellar void, to understand that the stars outside are not just navigation aids, but are ancient furnaces that forged the atoms in their own bodies, to recognize that the darkness between them and their destination is not empty, but is filled with the fabric of space-time itself, curved and warped by mass and energy in ways that make their journey physically possible, to find in the biology of their closed biosphere the same principles of interdependence and emergence and self-organization that characterize all life everywhere in all the ecosystems that have ever existed on any world, to understand that their small, difficult, bounded existence is not separate from the cosmos. It is the cosmos doing something remarkable. Gratitude is not a denial of difficulty. It is the capacity to hold the difficulty and the wonder simultaneously, to be honest about what is hard and to still be moved by what is beautiful, to be clear-eyed about the risks and to still find the journey worth taking. And here is the thing I want to leave you with as we reach the end of this series. Everything I just described, the capacity to think across time, to cooperate without a common enemy, to practice disagreement constructively, to feel genuine gratitude for the extraordinary improbability of consciousness. None of it is specific to a generation ship. All of it is relevant right here, right now on this planet, in the civilization we actually inhabit. We are already on a generation ship. We have always been on a generation ship. The Earth is a closed system, hurtling through space with finite resources and a life support system of extraordinary complexity that we do not fully understand and are currently stressing in ways that make even the most optimistic engineers nervous. We are already dependent on each other for survival in ways we mostly do not acknowledge. We are already making decisions whose consequences will fall on people not yet born. We are already navigating the tension between the freedom of the present generation and the obligations to future ones. We are already asking, whether we know it or not, what kind of people we need to be in order to keep the journey going. The generation ship in the interstellar void is not a different situation from the one we are in. It is the same situation made undeniable, made impossible to ignore, made so stark and so immediate that every question it raises is forced into consciousness, where it can be examined and answered rather than quietly avoided. And that, finally, is why I think the generation ship matters as a thought experiment, even if it never gets built, even if we solve the energy problem by finding a different approach to interstellar travel, even if artificial intelligence makes crude missions unnecessary, even if it turns out that the interstellar medium is so hostile that no biological beings will ever cross it. The generation ship still matters because thinking about it seriously forces us to confront questions about ourselves that we need to confront regardless. Questions about time and cooperation and conflict and meaning and gratitude and what we owe each other and what we owe the future. You have spent time with this video. You have followed the physics across light years and centuries. You have sat with the ethical weight of unborn generations. You have looked at the real science of radiation shielding and closed biospheres and genetic bottlenecks and relativistic time dilation. And I hope that somewhere in all of that, something shifted slightly. Not in your opinions necessarily, not in your plans, but in the scale at which you are thinking, in the time frame across which you are imagining, in the sense of how large the universe is and how small we are, and how extraordinary it is that we can know both of those things simultaneously. Because that shift, that expansion of perspective, is not just relevant to thinking about interstellar travel, it is relevant to everything, to how you vote and how you invest and how you treat the people around you, and what you choose to build and what you choose to protect, and what stories you choose to tell about where we are and where we might be going. Carl Sagan believed, and I think he was right, that the overview effect, the shift in perspective that astronauts experience when they see the Earth from space and understand viscerally how fragile and precious and isolated it is something that all of us need, not just the few hundred people lucky enough to leave the atmosphere, all of us. That the survival of our civilization may actually depend on enough people developing enough of that perspective, enough of that sense of the whole picture, to make the collective decisions that the situation actually requires. The generation ship is a thought experiment that generates its own version of the overview effect. You do not need to leave the atmosphere to feel it. You just need to sit, honestly, with the full picture. With the 4.37 light-years to the nearest star and the 13.8 billion years the universe has been running, and the 2 trillion galaxies in the observable universe, and the extraordinary, improbable, beautiful fact that you are here at all, made of stardust, capable of knowing all of this, take that feeling seriously. Do not let it fade when the video ends and the notifications come back and the ordinary world reasserts itself. Let it change something, even something small. Let it make you slightly more patient with the future, slightly more curious about what you do not yet understand, slightly more aware of the extraordinary improbability of being alive and conscious and capable of wonder on this pale blue dot suspended in a sunbeam. Because that awareness, that capacity to hold the scale of things and still find your own small life meaningful and worth living well, is not just what a generation ship crew would need. It is what we need, Right now, here, on the only home we have ever known, the stars are waiting. We are not ready yet, but we are learning, and that, in the end, is the most human thing of all. And if this video left you feeling the weight of the void, good, because it only gets worse. Click the video on your screen right now. Why space gets more terrifying the further you travel. Trust me, you are not ready for what is out there, but you need to know.